I am Tom Fitzpatrick, Technical Program Chair for this year. It is my pleasure to introduce a man who needs no introduction, but I'll do it anyway. Cliff Cummings is one of the premier System Verilog, UVM, and other verification methodology trainers in the world. He's also a really great guy. I've known him for longer than I care to admit. So without any further ado, Cliff Cummings, Sunburst Design.
Thanks, Tom. Well, good morning. Welcome. This title does not match the really long multi-line title that was there before. This is basically what it is. We're going to talk about IEEE UVM, and we're going to then talk about some of my favorite tricks. So when it comes to IEEE UVM, the topics that we'll cover in this portion will be just a quick introduction. Then we'll talk about some resources and references that are available to you, some very good resources. We'll talk about the most obvious question related to IEEE UVM. And then we'll talk about virtual classes and the UVM factory. We'll talk about UVM do macro replacement and UVM comparators and status. So just by way of introduction, I'm just kind of curious. Anybody here born after the year 1993? Anyone here born like 1994, 1995? Raise a few hands. Oh, gosh, man. I have conference papers that are older than you guys. So in 1993, I did 4 conference papers, and then you guys were born. Now, I don't think there's any correlation between those events, but oh, gosh, guys, really? If I ever teach an engineer who is younger than my oldest granddaughter, that's it. I've probably been doing this too long. I've already taught engineers younger than all 4 of my daughters, and now engineers younger than my conference papers. Oh, boy. All right. So when it comes to UVM and best known methods, what I always tell people is UVM's best known methods don't all exist. We're still making it up. So when you learn a best known method, don't let that dissuade you from trying something different. This conference right here is a great conference to be sharing some of the new things that you're trying in UVM, because what you're trying may become the new best known method going forward. So whenever I'm doing training, I'm trying not to tell people this is the best known method, you can do it no other way. I just tell them this is what we seem to all be doing right now, but if you come up with something better, I look forward to your paper at a future DVCon conference. So when a frequently asked question, what's going to replace UVM? In my opinion, nothing. I think UVM is there for the long haul. It's going to continue to be modified and updated over time. And so there will be modifications, there will be enhancements to UVM. And when it comes to the IEEE standard, that's some of the first set of enhancements, modifications to the UVM standard. But there's going to be complementary methodologies that come into play. PSS, the Portable Stimulus Standard, is going to become very important. And PSS will help to generate many of the UVM sequences. On top of that, you've got the UCIS, the Unified Coverage Interoperability Standard, which helps with the collection of coverage data. So there will be collaborative technologies that will be developed over the years, but UVM, I think, is just going to continue to migrate and to improve. I have my own preferences on what I'd like to see change in UVM going forward. So by way of reference, there were tutorials in 2017, there were tutorials in 2018 on the UVM standard by true UVM experts. You can go out to the Accelera webpage and register and watch these tutorials for free, and I highly recommend that you do so. And so there's the 2018 tutorial, there's the 2017 tutorial, and so you can go out, you can watch both of these videos of that were done by some of the experts in this field. In addition to that, there's 2 logins that you ought to get, 2 free logins. The first one is for the Accelera forums, and that login is free. You should register, get access to that login. And also, there are free versions of the IEEE standard. Now, it used to be that you'd go out there and you could just download the IEEE standards, but now when you go out there, all they do is they show you the standard. They don't let you download it unless you have an IEEE login. And once you have an IEEE login, which by the way is free, then you can actually download copies of these standards. But these are also linked from the Accelera webpage. So everybody ought to have access to the videos and these downloads and everything else. So when it comes to DVCon 2017, what you'll find in the back of this presentation, there's 5 slides that talk about what went on in the DVCon 2017 tutorials. And so on those slides, you'll find that I've kind of indexed to say which slide numbers talk about which features that each of the presenters talked about. Similarly, at the back, and we're not going to go over these slides, they're just all in the back of my presentation for your reference. There's also a 2018 set of slides to show you which authors talked about each of these topics. And again, I've kind of indexed where each author has talked about different topics within the IEEE UVM. And so in addition to the tutorials, the videos, you can look at these and you can find where they have talked about each of these different features. And so if you want to download the latest base class library, you can get that, again, from the Accelera webpage, and no login is required for that, but you can go out there and grab that. And the latest modifications were done just in November of this past year. And so you can just go get a copy of all of those libraries. Now, as far as 2017, there's a forum also out there on the 2017 methodology and base class library. And the very first question that was asked out there was by my good friend Brian Hunter. He asked the question, who can provide a summary of what is new and what has changed in the IEEE UVM standard? And the response came from Justin, where he was the Accelera UVM group chair. And Justin said, wow, starting the question off with a not entirely unexpected doozy. Now, for those unfamiliar with the technical term, doozy is kind of like humongous or really, really big. And so he says, yes, it's a big question we all want to know. Unfortunately, there is no single document which states here's a full list of everything that changed. This is because a large number of the changes were performed by the Accelera working group prior to the IEEE working group. But then he went on and he at least gave kind of a short list of his summary of what has changed. First off, the user guide was removed. It was just deemed not to be standard worthy, and we saw that also in the DVCon 2017 presentation, slide 10. He said added more set and get accessor methods to replace some of the current knobs. But the knobs are still going to work for you. It's just kind of a better software practice to use the accessor methods. Users can insert code into the UVM core services. It's an advanced topic and an example to create something like a factory debugger. And it allows users to make custom version of the libraries without hacking existing UVM. He also said library initialization ordering. Now, this was also an advanced topic, so you might be able to have parameterized classes participating in the name-based factory. Continuing, removing the black magic. That was Justin's words having to do with field macros, some of the undocumented behavior related to field macros. And so users could now implement their own field macros more safely. Policy class changes. And so all policy classes now extend UVM policy, and there's now a policy class for the copy commands and new printer policy classes to help you implement new types of printers. Registers. And again, Justin's words, surprisingly few changes in the register package in UVM. The most obvious being is that now you can unlock and relock the models to remove, replace registers at runtime. This can help support hot plugging and reconfiguration of designs. And then deprecation. As a matter of fact, Justin's presentation last year was excellent from the standpoint of, he said, there are a number of things that are being deprecated. How do you go about checking your code to make sure that you can pass after all the deprecation has happened? So there's a number of steps, in the 2018 DVCon presentation walked you through those steps of recommendations of how to make sure your code is going to work just fine. As far as the DVCon Accelera resources go, registration and viewing the videos is free. And Justin also referred to the 2017 and 2018 DVCon presentations. And you'll find that these authors spoke at the 2018 DVCon and the 2017 DVCon. And Justin said, aside from number 1, that we'll show you again in just a moment, most of the changes are for advanced use cases or providers of infrastructure. Day-to-day users should not necessarily see a drastic change. Number 1 being adding more of the set and get accessor methods. That's one that you could very likely use. So multiple features were shared in these tutorials. They were very complex. A number of the examples were very complex enhancements that were shared. And so personally, I never tried to implement the corner case functionality, some of the advanced features that were shown in the past 2 years. but some of those examples were a little difficult to understand. You need time to read them and review them to fully understand what the authors were talking about, except to the presenter. To the presenter, it was clearly obvious what each of these was. Yeah, I personally barely followed many of the complex examples, so I could re-show the examples that were in the past two DVCons. And I could show some of the advanced corner case topics that were discussed in those DVCons. I'm not going to do that. I'm not going to rehash something that's already out there that you can review. You can watch the videos, you can download those slides. Instead, I want to show you some of the mainstream enhancement examples and how I can use them in UVM. So now you can register and watch all of these features. And if you're doing anything tricky, I recommend that you do just that. Go watch the videos of these DVCon presentations. And so what happens is when you see those slides and hear the presenter always shares more than what is on the slides. And so I recommend not only getting the slides, but listen to the presenters because they'll include a few of the finer points that isn't on their slides. So I'd recommend that you do that. And if you're doing anything complex, it's worth a listen to the existing DVCon presentations. So basically, this is my way of saying that these guys are really, really smart, and I'm really average. And so I want to show you some of the enhancements and features that the average coder can use inside of UVM. And where appropriate, I will be listing the DVCon slides from the 2 previous years so that you can reference from those slides what I'm talking about. And I also want to show you a few of my favorite tricks a little bit later. So probably 1/3 of the presentation it has to do with IEEE UVM, and 2/3 I decided if you're going to spend time with me for the next 3 hours, yes, I said 3 hours. If you're going to spend time with me for the next 3 hours, I want everybody in here to be able to walk away with perhaps some new trick that they haven't tried inside of UVM. So I'll be sharing some of my favorite UVM tricks as we go through. So first off, let's start with virtual classes. Virtual classes are only intended to be a base class. There's not enough functionality in a virtual class in order to use it as a standalone constructed object. And so most UVM components must be extended in order to create something useful that you are going to use in your UVM test benches. Virtual class methods can be virtual or non-virtual. A non-virtual method means that the extended class can override and change the prototype. And when we say prototype, what we're talking about is the method, the function or task header. And so if it's a virtual method, usually the easiest thing to do is just copy that header into your extended class and then start modifying that. And it also makes polymorphism possible so that you can assign extended handles to base handles, and then when you execute base class methods, it looks like you are executing the extended methods. Virtual methods create placeholders with a required prototype. That same function header can include default implementation if the extended class does not override the method. So when it comes to virtual classes can have virtual methods, and virtual methods make upcasting and polymorphism possible. System Verilog 2009 added pure virtual methods. It's just like a virtual method, but it requires the same prototype. But unlike virtual methods, there can be no default method implementation. It's just a placeholder inside of your virtual class. Pure virtual methods require extended classes to override that method. So the extended class must provide an implementation to anything that was declared as a pure virtual method in the base class. The pure keyword is only legal inside of virtual classes. You don't use the pure keyword inside of a non-virtual class. So let's look at a little example here. We've got a virtual class, and inside this virtual class, we've declared a pure virtual set A method. And so with that pure virtual method, the pure virtual method means it can only be the method prototype. Once you say pure, you can't have a body for that method, not even end function, end task. All it is a prototype or the function header. In the extended class, once we extend that virtual class, we are required to provide the implementation. So a pure virtual method basically imposes the requirement that whoever extends that virtual class is required to provide the implementation. And pure is only legal inside of virtual classes. To take the example just a little bit further, if I start off with a virtual class, and if in my virtual class that I've called VC1A, virtual class 1A, I have declared a pure virtual method. That's just a method prototype. If I extend the virtual class with another virtual class, I am not required to provide an implementation for the set A method. But once I start extending the derivative virtual classes, now I am required to provide the implementation. So the first non-virtual class that extends these virtual classes is required to provide the implementation. On the other hand, if I have a virtual class with a pure virtual method, and so I've defined a pure virtual method in the second virtual class, I can extend the virtual class, and I can provide a method in the extended virtual class. Once I've done that, then once I get out to a non-virtual class, I am not required to provide the implementation. It is optional at that point whether I want to provide the implementation or not. So that gives you an idea on pure virtual methods. Probably the most common example that we use inside of UVM is the UVM subscriber. UVM subscriber has, in the base class, has a pure virtual write method that we're required to implement for analysis implementation ports. And so prior to pure virtual, how was this handled in class-based verification methodologies? Well, what you would find is in the base virtual class, you would find some type of message inside of the virtual function that said, error, the virtual method has not been implemented yet, and it would abort the simulation. And so it's kind of UVM-like, but it's not a pure virtual method. And VMM had some of these in that class-based methodology. But when you compare virtual to pure virtual methods from a base class, the virtual methods, the missing implementations were not discovered until runtime. Then you'd get the runtime error saying that the method had not been implemented. Whereas a pure virtual method, this is found at compile time. And so we find it much sooner, and it means that we can fix this much quicker. And that's some of the value of these pure virtual methods. Okay, so now let's get into why I'm talking about this with respect to IEEE UVM. Because there are a couple of user-defined classes very common in a UVM test bench where we build a base class that really is not intended to ever be constructed itself. One of those is frequently the test base, where you'll put in all your common test functionality, and then all of your tests tend to extend the test base. So you'll have a test base that extends UVM test, and then your tests will extend the test base. A second common example is the virtual sequence base class. The virtual sequence base class is what is going to retrieve and check the handles from the virtual sequencer. And so we typically have a virtual sequence base class that does all the hard work, all the heavy lifting, and then we extend the virtual sequence base class with our virtual sequences. In UVM, these cannot be virtual classes. The test base, the virtual sequence base, cannot be virtual classes. And yet that's probably the right type of class for those to be, anything that's a base class. If you try to do that, you're going to get the typical error, an abstract class cannot be instantiated. And so what happens is it looks and it says it's going to try to build one of these virtual classes. Of course, you cannot new construct a virtual class. So we've never been able to declare our own virtual classes and place them inside of the factory. Okay, so an enhancement in IEEE UVM. For our objects, we've always had the utility macros for classes, the object utils begin end, the param versions as well. Now with IEEE UVM, you're also going to have UVM object abstract utils, UVM object abstract utils begin, etc., so that you can now declare your classes to be virtual classes and place them in the factory. And so these macros will make it possible now in this example for me to create a virtual sequence base and place it in the factory and make sure that it's a virtual class that nobody can construct on its own. And so now I've got these virtual classes with I can put pure virtual methods inside of the factory as well. Because remember, pure keyword is only legal inside of a virtual class. Second, for components, we've always had component utils begin end, and with params, etc. Now you also have UVM component abstract utils, UVM component abstract utils begin and end. And so it means that you can now put virtual base classes also into the factory, such as the test base. And so again, we can use a pure keyword, but with these abstract utils, we can now put our own virtual classes into the factory. In UVM 1.1, we were allowed to access the factory handle just as is. And so we could just make reference to what I frequently do inside of my test base, as a matter of fact, is I will put in the start of simulation phase. By the way, I think of start of simulation as just being the pre-run phase. What do I want to do just before I start running my UVM test bench? I could say this.print to print out what is the test bench structure of my design, and I could put also factory.print to say what are all the classes that have been registered with the factory. And so if I'm doing any debugging, I frequently will turn that on, turn up the verbosity, so that I can see what my test bench structure is and what has already been registered with the factory. UVM 1.2 and IEEE UVM requires the declaration of a factory handle, but it's really very simple. You're going to declare a handle of the UVM factory type, and so here we just use the clever name factory equals UVM factory, the static method call to get the current handle of the factory. And so once you use the static method, now you have a factory handle that you can use, and you can still do the same thing that you used to do with UVM 1.1D. And that is in the start of simulation, I can still print out the test bench, and now I can print out what is inside of the factory as well. UVM do macros. Now, this is probably one of those places, if you're using the UVM do's, this is one of those places where you're going to see a number of changes. So when it comes to UVM do, what they are allowed to do is they're allowed to execute either an item or a sequence. And so the UVM do's do a quick check to find out, am I working with an item or am I working with a sequence? And then they perform the creation, the start item, the randomized, and the finish item. That's all built into the UVM do macros. You also have UVM do on to say you want to run these on a particular sequencer. And you have UVM do with priorities to say that you'd like to execute some priority with these UVM do commands if you have multiple commands going to the same sequencer. And you also have UVM do with, so you can put in inline constraints using any of these macros right here. And so very commonly used were the UVM do and UVM do with inline constraints. If you're using virtual sequencers, you frequently use UVM do on or UVM do on with. And less commonly used, but they're out there, are the UVM do with priorities. Now moving forward, you still have a UVM do command inside of IEEE UVM. But there is no UVM do with. That has been deprecated. As a matter of fact, as you go down that list, everything else in that list has been deprecated. You are now going to have just one UVM do command. But the UVM do command takes all of the arguments and has default values so that you can execute all the other UVM do commands that you've been used to in the past. Also, in UVM today, you have these macros. I don't see these used quite as often. I see the UVM create used rather frequently. But if you look at this, again, they all work with a sequence item or they use a transaction. And the creates just do the create portion, the type ID create command for that transaction. And then all of the rest will do start item, finish item, and some of those will also do the randomization. So it's basically the way to do the same thing that we saw on the previous slide, but in multiple steps as opposed to just one step. And again, the UVM create is the one I've seen engineers use as opposed to using the type ID create command. So again, you have UVM create, that is still there, but in IEEE UVM, the next create command has been deprecated. We still have UVM send, but you don't have UVM send priority. You have the UVM rand send, which replaces the last three that you see on that list. And so these are the new UVM commands. You now just have 4 instead of what was previously 16 UVM type commands. So how are these things used? Well, you do UVM do, and then you pass up to 4 arguments to the UVM do command. And it currently has just defaults for most of those arguments. So in 1.2, you might say that you're putting together some virtual sequences. You're doing an AHB sequence on the AHB sequencer or the Ethernet sequence on the Ethernet sequencer. And if you're doing the transactions with a constraint, then you'd say UVM do with, you do a transaction and set a constraint as you're running that particular command. Now with IEEE UVM, the commands are still going to look pretty much the same except they're UVM do's instead of UVM do on. And so for the virtual sequences, that's going to look the same. But if you're going to add constraints, then you need to leave a couple of spots open for the other arguments. And so you throw in a couple of commas. And before you ask, no, you cannot pass by the arguments by name. And so it is by position. So if you're just doing a UVM do with a constraint, you'll have a couple of extra commas in there for the fields that you're not particularly using. Okay. And in addition to that, you have the UVM create and the UVM send, the UVM ran send commands. They also have default values assigned so that they can be used as well. So you've gone from 16 UVM do commands down to 4, the most common being the UVM do command itself, which replaces what was 8 commands in IEEE UVM. Removed from the IEEE standard is the UVM comparator, the UVM algorithm comparator, and the UVM in-order comparator. According to slide 51 in the 2017 presentation, these were deemed to be not standard worthy. And so I've talked to a number of people over the years that said they've had problems with these. In general, they work pretty good, but when they don't work well, then it takes a little while to fix it. These comparators are easily implemented by engineers themselves. I know I do it all the time inside of scoreboards. By the way, they're not deprecated. The source files are still there. They're out there. But there's some of these. And so what I've shown you so far are some of my favorite of the UVM type enhancements. Like I say, go out and watch the presentations from DVCon 2017 and the presentation from DVCon 2018, and you'll find some very advanced features if you'd like to take advantage of those inside of UVM. So now I'd like to talk about a few of my favorite topics. And here's where hopefully I can share something that somebody can take away so that it was worth your while to come out here on a Monday morning. So we're going to talk about UVM transaction. We're going to answer the question, why is this a class? I wish somebody had showed me this when I was first learning OVM or UVM. We'll talk about UVM do methods versus field macros. We'll run a comparison between those. We'll talk about start item, finish item versus UVM do as well. We'll talk about the messaging macros and a few tricks and guidelines related to those. We'll talk about UVM factory and factory print type trick that I frequently use. Then I'm going to spend a good chunk of time talking about analysis paths to clarify how they work. And we'll also talk about basically how they're implemented under the hood. It will not be UVM code, but it'll show you how these things work. And we've often found that it's very useful. If you understand how it works, you typically use it better in your UVM test benches. So the UVM user guide, once I learned this really helped me to understand the examples that were out there, because I didn't understand why the examples didn't seem to match up to each other until finally some of the experts were able to share with me these points right here. The user guide. When you read the user guide, this was written by Cadence engineers, and it teaches Cadence recommended methods. Perhaps just a quick sidetrack here to give a quick, very adulterated version of where OVM and UVM came from. Some time back you had VMM. And it was a virtual methodology manual written by Janik Bergeron and people at Synopsys and his co-authors. And the VMM was becoming the popular verification methodology. And the VMM, the Synopsys would tell you that it is not proprietary, it is licensed. Now to me that means it's proprietary, because most engineers don't have legal authority at their companies to sign any type of license to see the internals. And so to me it was basically proprietary, even though it was only licensed. Next, you had Mentor that came up with the AVM, the Advanced Verification Methodology, and you had Cadence that had the URM, the Universal Reuse Methodology. Well, Cadence and Mentor got together and said, let's gang up on Synopsys. And so they said, let's put our methodologies together, and we'll call it the OVM, the Open Verification Methodology. And all the class libraries will be completely open. Anybody can have access without signing any type of license for it. And so that's what they did. But the two methodologies, the Cadence URM used more of the macros, the Mentor one used more of the methods, and so most of it came together, but there are a few little flavor differences between the two. OVM started to take off. It started to win the verification battles, and so Synopsys comes along a little bit later and says, okay, well, we'd like to join the party. We'd like to be part of this. We will donate the register package. We'll donate command line processing into this if you'll let us be part of the party as well. But we don't want to admit defeat, so let's give it a new name. Let's call it UVM for the Universal Verification Methodology. And so to save a little face, we get UVM, and the biggest difference between OVM and UVM is the first letter. Okay? You go into the OVM object file, and guess what? It's called UVM object in UVM. There were a few differences, a few very nice enhancements that came along, but it was mostly a one-letter change, and it was mostly so that Synopsys didn't have to admit defeat. Probably some 8-9 months later, Synopsys comes along and says, and we now support OVM. It's like, you guys, you should have just done that to begin with, because there were OVM users out there. There's still OVM users out there that still haven't completely migrated to UVM, because it takes some work, and it would have been nice just to call it OVM to begin with. But we have UVM. But this is also partially going to explain why there's two flavors of UVM, because it came from a Cadence background, it came from a Mentor background. And so when you look at the user guide was written by Cadence. And the user guide has a large number of macros used inside of that user guide. And so it does use a large number of macros. It's using the Cadence recommended methodologies. And then you've got the Verification Academy tutorials out on the Mentor webpage. And this teaches more of the Mentor styles, fewer macros, more of the methods, using the methods instead. And then some of us also found the old OVM cookbook. There was an earlier version also written by Mentor employees. Well, the problem was the user guide, the cookbook, and all these other sources didn't tell you that there's another way of doing it. And so when you read the user guide, you'd look and you'd say, that doesn't match up to what I'm seeing in the Verification Academy videos. And you'd watch the videos, and that doesn't match up to what's in the user guide. And so engineers were left wondering, which one has the bug? And actually, they were both right. You just had to know whether you're using more of the macros or whether you're using more of the methods. It would have been really nice had the user guide said, we prefer to use the macros, but you can do this with methods. It would have been nice if the videos had said, we prefer the methods, but you can also do this with the macros, so the engineers would have known there's another way. I think that the vendors kind of thought, oh, they'll read our user guide or they'll watch our videos, and they'll never even try to find the other one. Well, as users, we found them all. We all found those. Not only that, we found the source code, and since it was hard to learn, we all dug into the source code too, to figure out how OVM and UVM were working. And the other problem is the authors of all these materials that are really, really smart software guys. I mean, these guys are top of the line people that put these methodologies together. And they just assume that when you read these things that you're already an expert at system Verilog, object-oriented programming, and polymorphism. And now they're going to take you to the next step of UVM. That's not a fair assumption. And so many of the authors, they just kind of forgot what it's like to be idiots, like me. And how do I learn this thing on my own? And so that explains, if I had known that up front, then I would have spent less time wondering, okay, why does this not match what's over here? Once you see the two flavors, there isn't that much difference between the flavors. And then you can go out and look at any example on the web and say, they're doing it more the Cadence way, they're doing it more the Mentor way. And you'll understand what the example is doing. So let's talk about transaction-based classes just a minute. So transactions are driven onto the DUT interface, frequently as sequences that can be built up from a single transaction, from multiple transactions, from multiple other sequences as well. And so when it comes to the transactions, this is the other question I didn't understand when I was first learning class-based verification. That was, why am I using classes? Why am I not using structs? I know what structs are. I'm very familiar. I'm very comfortable with structs. Why are these things classes that are being passed around? And it was this analysis right here that helped me to understand why I want to use classes. First off, for classes, they're dynamic and have multiple fields. For structs, they're static. They also have multiple fields. That's what I was familiar with. Classes can have randomization fields. No rand fields inside of a struct. You're going to have to declare the randomization yourself. Classes have randomization constraints. So you can say, when I create one of these things, constrain the randomization to certain areas. But structs, no randomization constraints. You're going to have to handle that manually yourself. Classes have built-in methods, such things as copy, compare, print my contents type methods that come right along with the class. No built-in methods for a struct. Classes, you can generate as many as you need at runtime as you're running the simulation. With structs, you're going to have to figure out how many you're going to use, make sure that they're all declared and in place to use. Classes can be extended, so it's very easy to create extensions and hierarchies of classes. Structs, you have to copy the code and then modify the code in what would be the extended version. Classes can be in a factory for runtime substitution. No factories for structs. So what it comes down to is classes are basically dynamic, ultra-flexible structs that can be easily randomized, easily control the randomization, and created whenever they are needed. That's why we use classes for verification methodologies. And so the default that we use is we extend the UVM sequence item in order to create our transactions. So when you start passing transactions and signals through your UVM test bench, you're passing these transactions around, and the more you get into UVM, the more you realize that really smart people did really smart things. Because you're going to pass around this object you call a transaction, and it might have 2 signals, it might have 1,000 signals in it. No matter how many signals are in it, your UVM test bench looks pretty much the same until you get down to the sequencer, and then the driver grabs one of the transactions, and now you got to split it up. Now it does matter whether there's 2 or 1,000 signals. You've got to get them all split up with the correct timing, going out to the buses. But what you've done is you're passing around this transaction, and the other part that I didn't understand when I first learned this was, okay, I need an input transaction and I need an output transaction. One to handle the inputs, one to handle the outputs. But in UVM, the way things are done, you just declare transactions that have all the inputs, all the outputs, and then you decide whether you're going to use them or not. But they're all right there in that transaction. And so you get down to your driver, and the driver drives all of the transaction inputs off into the .dot interface and completely ignores the outputs that have been declared inside of there. Because of that, the recommendation is if you're doing some type of design that has inputs and outputs as opposed to something like packets, you just do not randomize the output fields. You don't declare your output fields to be randomizable. The inputs, yes. The outputs, no, because it'd just be a waste of time. Once you get down to the driver, you're just going to throw away the outputs, use the inputs to drive into the .dot interface. And then finally, the monitor is going to sample all of the inputs and all of the outputs with the correct timing. Here again, it matters whether there's 2 signals or 1,000 signals. The timing has to be accounted for. It's going to sample all those signals, reassemble those into a transaction, and pass that transaction through an analysis port, broadcast it up through the output of the monitor, and it'll eventually end up as something like a coverage collector, a scoreboard, and any other components that you have up in your environment right there. And so on this one, we are going to take advantage of both the inputs and outputs. But once you get into the scoreboard, typically you have some type of prediction mechanism. And in the prediction mechanism, again, you ignore the outputs. You just look at the inputs to predict what the outputs should have been. And then on the comparator side, it typically ignores the inputs. It just says, I'm going to take the outputs that I've sampled and compare those to the predicted outputs from the predictor in order to prove that this design is working or not. And so you've got these transactions that have all the fields in it. You don't need separate input and output transactions. And because of that, once you get into UVM a little bit, you find out most of this UVM test bench is just a template, a set of template files. I can recreate the same thing over and over again. And that's what I usually do in UVM. I just have a template directory of UVM test bench files, and then I have a list of 8 files that need modification, and I keep it on my wall, right above my computer. And when I'm ready to put together a new UVM test bench, I just do a VI on all 8 files so I can modify and go to the next one and modify again. And so it's once you get into UVM and once you see how it works, you discover, gosh, I'm doing the same thing over and over again, at least the block level. And this really isn't so hard. It just takes a little while to get used to some of the new things about this verification methodology. So let's talk about standardized UVM formatting, and this is my preferred style. And so you'll find it used differently in the examples that you see out there. But I tend to put together all of my components and transactions and sequences, and I declare things in this order. So if I'm using the field macros, then I have to declare all the transaction variables right at the very top. I don't have to do that if I'm using the methods instead. Then I register the class with the factory. And if I'm using field macros, then I declare the field macro flags at that point right there. I declare variables and cover groups if used. I'll declare virtual interface. I'll declare ports and components. So if used, It's your components that are going to have the virtual interface, and they're also going to have the ports and other handle declarations. You're going to put in a standard boring new constructor that goes into any of these. There's basically only 2 types. And then you've got all the phases that you need to do. You need to do the build phase, the connect phase, other pre-run phases, run phase, and post-run phases. And you also have your common class methods. So you have all of these pieces here, but if you're doing components, then those are the ones that have the phases in them. Something else that I did not understand well was the phasing inside of UVM. And Tom, bless his heart, he worked a paper with me, and he was very patient with me as I tried to talk about, okay, there is the run task, and there is the run phase, and Tom finally said to me, Cliff, those are the same thing. He's like, oh, of course. Once you realize what you're doing, when you code up these phase methods inside of your components, all you're doing is you're saying, because the phases are going to be executed in that order. And all you're saying is, once we get to like the build phase, I want to be a participant. And so when you code up a build phase, all you're saying is, in the build phase, I have something that needs to be done. When we get to the connect phase, I want to be a participant. I have things that need to be connected. And so when you get to these phases here, and that's when it finally dawned on me, okay, I'm coding up all these phase methods, but I never call them anywhere. So I'm coding these things up, and all you're doing is saying, I want to be a participant when we get to this phase. And once I made that realization, thank you, Tom, then all of this made a lot more sense. You're just coding up things that will be executed when the phases are executed in the proper order. And that's when I finally realized, yeah, that's right, I'm never calling these things. And so all you're doing is saying, I want to participate in this phase when we get to that phase, when everything is being built and connected and everything else. And so you've got 2 ways to implement your transactions. And here's where we're going to get the 2 flavors that you find. The first flavor is more the Mentor Verification Academy style that uses the do methods, where you register your transaction with the factory, you declare your variables, you put in your common new constructor, then your common transaction methods, such as convert to string, and then you'll add things like do copy, do compare, and other do type methods. Then you've got the field macro style. This is more the Cadence user guide style. And so this is what you see inside of the user guide, where the variables have to be declared at the top, and then you register it with the factory with the field macros for each of those variables. You'll have a begin and end version on the registration. Then you declare your variables, and you'll also put in the common new constructor. Then the common base transaction methods, you still code up the convert to string, but all of the rest of the do copy, do compare have been absorbed into the field macros themselves. And so if you're using the do method, you're using UVM object utils right at the very top, and then you're going to declare your variables underneath that. If you're using more the field macro style, then you're going to declare your variables at the top, and then you're going to have object utils begin, object utils end, where you say what are the field macro flags for each of those variables. And so there's where you see the object utils versus object utils begin type usage. So standard transaction methods. You have standard transaction methods, and these are all defined in UVM object. Now, most of us know that UVM object is the top-level base class. There's something above it called UVM void that nobody ever uses. But UVM object is the top-level base classes, and that's where all these standard transaction methods are defined. Most of them are empty, but they're defined at the top level, or somewhat empty. Copy and compare, I find those to be very important methods. The print and string print are somewhat important methods. I tend to use the convert to string myself. Pack and unpack if you're doing any type of serial to parallel type implementation, and record in order to do debugging of your transactions. 3 more transaction methods that you find are the create method, auto-generated by object utils, the clone method, which does a create and copy, and then the convert to string, which currently only returns an empty string, but it is in that top-level base class. And because it's there, any extended class can make an assignment to the base class and call these methods using a base class handle. So when it comes to common usage, we've already talked about sampling all the signals back into a transaction and passing them up to the coverage collector and scoreboard. In the coverage collector, in the predictor, you typically take a copy of the transaction. because you're going to modify the outputs based on what the inputs are. You're going to say, I expect the outputs to be these values based on these inputs. And you never want to be modifying any of the fields of the broadcast transaction, because all the devices are looking at the same handle. They will see the updates as well. And then the compare method, once you put a compare method into your transaction, you've basically said that these are the fields that are most important to me. You can add more compare methods later, but these are the fields that are most important to me. And once it is there, it makes the comparator very simple code inside of your scoreboard as well. So each transaction should include important methods. There's two ways to implement those methods. You could use the field macros, and this is what's shown in the user guide. And they're simple, but they can be inefficient in simulation. Cadence recommends using these. Mentor recommends avoiding these. Then the manual coding, this is what you find inside of Verification Academy. So these are not too difficult. They're more efficient in simulations. And Mentor recommends using these methods instead of the field macros. By the way, both work. And so with standard transaction methods, these are the methods that you're going to call. You're going to call copy, compare, print, all of these right here. You never override any of the standard methods. You call them, but you never override them. Then there's two ways to add functionality to these methods. The first one is using the do methods. And for the do methods, you override each of these methods right here. Well, you'll add the object utils, and then you'll do an override on the do copy, which is called by the copy command, the do compare, which is called by compare, et cetera, et cetera. So when you implement each of these do methods, each of these are now being called by the standard transaction methods. You never call the do methods. So you call the standard methods, you never override them. You override the do methods, but you never call them. Then the second way that this can be handled is using the field macros. And with the field macros, you use UVM object utils begin and end, and you put in a field macro for each of the variables in your transaction. And those field macros actually create a very large function that is called by each of these commands right here. It calls the exact same function, but then it tells the function, okay, I'm doing the copy command in this function, or I'm doing the compare command inside of this function. But it's a common, very large function that is being called by each of them. If you're using the do methods, you're still going to override and call the convert to string. And the same is true if you're using the field macros. You're still going to override and call the convert to string. That is not automatically populated by the field macros. So let's talk about the compare a minute. You don't want to override the built-in compare method. Okay? So why not override that compare method? Are you kidding me? Have you seen how much code is inside of that UVM object compare method? The base compare method has 69 lines of code in it. And your code goes right there in that compare method. You are here, sort of thing. And so what you have is you've got 57 lines of pre-compare code in that compare method. Then it calls that function, if you're using field macros, the very large function, or it calls, you could do both, you shouldn't, but you could, and then it calls your do compare method. And that's what you have done an override on, is the do compare method. And now that is going to be called on line 59, 58 if you're using the field macros. Then you still end up with 10 more lines of post-compare code. And so it'd be just way too complex, too many opportunities for mistakes if you ever did an override on the compare method. There's too many things that can go wrong if you start touching that code. That's why you've been given hooks for something that can be called by that code, but you're not supposed to touch the compare code itself. So UVM object utils, the definition of this, most of us when we got into OVM, UVM, we just thought, well, don't really understand it. I'll just go into the source code and figure it out. Okay, that was a bit of a folly because the macros are about 4 levels deep inside of there. So you've got this macro that calls this in different files. But one of those macros is the UVM object utils macro. And the definition of that is it calls UVM object utils begin, which is the code for the definition you see right below it. And also, it calls UVM object utils end. And if you look at UVM object utils end, it's nothing more than the keywords end and end function to close off that very large field macros function. And so the UVM object utils begin. That's where the registration with the factory takes place. It also builds that create function for you automatically. It also defines the get type name method. And then it calls UVM field utils begin, which is the first 20 lines of that really large function that I was talking about. And then, of course, once you do UVM object utils end, it closes off the begin and it closes off the function. But then each field macro that you call adds code to that very large function. And so when you call UVM object utils begin, all you're doing is closing off that very large function that exists inside of UVM. Every time you call UVM field int, you're adding 59 lines of code to that function. So for each and every variable that you call, it's 59 lines of code. What it is a great big case statement. It's a great big case statement because it's the same case statement that's put in the copy, the compare, all of these, because it goes into the case statement and it says, is this a copy command? Yes. Did somebody say no copy? Yes. So abort or execute the copy. Is this a compare command? Yes. Did someone say no compare? Yes. Abort and keep running. And so it's this huge case statement for every variable in your design. If you put in 10 UVM field ints, you're adding 590 lines of code to this function. Now, the field macros, let me kind of give the pros and cons on each right now. The field macros just work. I don't think I've ever had problems with them. It does everything for you. It's an awful lot of code. My biggest concern with field macros has been, usually the field macros work, but something in my code doesn't work. And so what do? I start single-stepping through the code. And if you don't know what you're doing with the single-stepping, all of a sudden you're going to step into each one of these case statements. And you're going to start walking through these case statements, and you're going to say, I don't recognize this code. And you don't. It's huge. It's really hard. And all you've done, you've gone through the first field, then you go into the next case statement. And you start single-stepping. So the field macros work fine, but if your code doesn't, the single-stepping gets to be a little bit of a nightmare to debug these things. On the other hand, the methods require just a little more coding, but it's your code. And so when you single-step, you know what you're doing in your code as you walk through each of those do type methods. So that's kind of the upside on each. The field macros, easier. The do methods, a little more work, but more efficient and easier to understand. Overriding the do methods then. So when it comes to the do methods, again, those are the methods that we call. You never override them. For the do methods, we use UVM object utils, and this is what you override. You override the do copy, do compare, do print, all of these different do type methods. And you never call the do methods yourself. You will override and call convert to string, because the built-in convert to string just returns an empty string. Later, we'll talk about the field macros and how those are used. But when you get into these do type methods, you need to understand a little bit about upcasting and downcasting inside of any class-based language. And so remember, UVM object is the top-level base class, at least the one that we care about. Then beneath that, you have multiple different levels. You get down to the UVM sequence item. And UVM sequence item is what we are going to extend to create our transaction type. And so for the UVM sequence item, it is a derivative of the UVM object. And remember, you can always copy an extended handle to a base handle. So I'm always allowed to copy a transaction handle to something declared as UVM object. But you need to understand how that's going to work and what you have to do because of that. And so here I have a transaction class that I put together. And let's just assume that I've already created an object and I've given it the handle name tr1. So I have this tr1 transaction object, and I want to copy all the fields from a T object into the fields that I've defined inside of my tr1 transaction. And so the T handle is pointing to another object that has certain fields that have already been defined. And I want each of those to be copied to my local tr1 transaction. And so when I do this, I'm going to call the copy command. That's what I will call. And it is going to call the do copy command. Now, the do copy command that I have defined inside of my transaction here has these 3 lines of code that, to me, kind of looked strange until I understood what they were doing. As a matter of fact, it was Adam Erickson's paper back in 2011. Very good paper. Highly recommend it. You can get that one off the Mentor webpage out of Verification Horizons. Do you know anything about Verification Horizons, Tom? Yes, a little bit. Okay. But you can still find that paper out there where he talks about the methods versus macros. Of course, just be aware, that Adam has a very strong preference for the methods, and so you'll see that in the paper, but it's very good. He had examples like this that I didn't fully understand when he first presented them, those first few lines of code. See, the problem is once you copy a transaction handle to this header, because the do copy is a virtual method, so you have to keep the exact same prototype. I can't change the type that's being copied into transaction. It has to stay as UVM object. So I'm going to copy a transaction into this, and when that happens, an upcast operation takes place. I can always copy an extended handle to a base class handle, which is what I'm doing right here. And now I have an RH handle that is pointing to the object. The problem is the RH handle is a UVM object type, so it doesn't know that there are data fields in there. They're all there inside the object, but it doesn't have access to any of those data fields. And so what you do inside of your do copy is you declare a handle of the transaction type that you care about. I'm really trying to copy one of these trans1 transactions, and I'm going to copy it to a local handle called tr inside of my do copy. And then I'm going to do a downcast operation, and a downcast allows me to cast a base handle to an extended handle. The cast operation does a type check to make sure, okay, what you are actually casting here, was it originally a transaction type? So the cast does a quick check to find out if this operation will even be legal. And if it is, and we know it is in this example here, then it is allowed to do a downcast back to a transaction handle. And once I have the TR handle locally, I now have access to all of those fields again. This happens over and over again inside a UVM. And so here, when I do the copy operation, now all I do is I take all the data fields out of that transaction that I've declared locally. They're copied to each of my local fields. And so now I have a copy of everything that was in the T transaction. And so this is part of the upcasting and downcasting. And whenever you do these do type methods, you're working with these prototypes that cannot be changed. So you're frequently declaring a transaction handle of the type you care about, and you're casting the RHS handle, which is a UVM object, back to the type that you care about. Now, before I go to the next slide, notice here that in the do copy, I've called the transaction handle TR. And so in this example right here, this is one that I use frequently inside of scoreboards. I've got a scoreboard calculate expected function where the transaction has been broadcast from the monitor up through the agent over into the predictor inside the scoreboard. And then I declare my own local transaction handle, and I create a transaction. And so when I create the transaction, then I need to copy this broadcast transaction to my local one so that I can now modify the expected values inside of the transaction. And so once I do that, I call the tr copy, and that is going to call the do copy method inside of my transaction. And the do copy has that virtual prototype, so I can't change that. And that's why I will do the declaration of my local transaction handle, and I will perform the cast operation to convert what turned into a UVM object back into a transaction. So when you use the do methods, you frequently have these couple extra lines of code at the top of the do method to say, give me the transaction type back that I passed to this method. So all the fields of the T transaction are now being copied to the transaction here. I typically then, in calculate expected, figure out what the new outputs should be. I place them in my copied transaction. And so those will be copied right there. And then I'm going to return the transaction back to the predictor, which will then broadcast it over to the comparator. And so I'm taking advantage of this upcasting and downcasting inside of UVM in these do methods. Now again, let me focus in on that do copy. Notice that I declared the handle TR for trans1. You're going to see many examples out there in industry where instead of using TR, they use RHS underscore. And it's perfectly fine, and it works. But then it means you're casting RHS to RHS underscore, and you're referring to RHS fields and RHS underscore fields. To me, it's really hard to track those, to track those and keep them separate. Because now I'm going to start accessing RHS underscore fields. And you guys saw me put on the glasses earlier. Well, that underscore disappears really quickly for me. And so it's really hard for me to track that. Our own personal preference is that instead of RHS underscore that you'll find in many examples out there, use a very distinct name such as TR so that you can distinguish between the RHS and the local version of the handle. Okay. So we've got that guideline that we always share, declare the local handles to be something distinct, not RHS underscore. You can't change RHS at the top. That's part of the prototype. You cannot change that, but you have a choice on what name you use inside of the do methods. Okay. And so when it comes to methods such as do copy and do compare, here's just two common examples. What you find out is you've got the required prototype at the top, and then you declare your own transaction and you cast the RHS handle to your local transaction. That's basically template code. And so in my template files, I already have that coded. I've already got the end function there. So all I need to do for the do copy is to add all the fields that need to be copied from one to the other to my do methods. Similarly, for the do compare, without going into all the details of what those arguments are, same sort of thing. I have template code right at the top. The do compare does have to return a value to tell you if it was equal or not. So it has a couple of extra pieces there. And then you get down to the bottom where you have the return the equal bit and the end function. So once again, a large portion of that do method is just template code. And then you say which output fields you want to run comparisons against inside of the do compare. And so the do methods, they do require more code than the field macros. But if you've got those in a template file, as I do, it typically isn't that much more code than using the field macros. Both have their advantages. Using the field macros then. Again, we've talked about the standard transaction methods. You do not override them. And then if you're using field macros, you have UVM object utils begin, UVM object utils end, and you've got a field macro for every variable inside of your transaction. And these, again, populate all of these commands. Well, actually, each of those commands is calling that huge function, that huge field macro function with a large case statement for each variable. And so there has to be that large case statement to represent each variable, and it's going to go in and say, am I doing a copy, a compare, what am I doing? What type of operation? And so it can perform any of those operations right there. You still have to code up the convert to string yourself. You do override that one, and you call that one directly. And we've already talked about the do methods. That was shown earlier. So looking at field macros, what's required for the field macros? If you're using the field macros, you declare all your transaction variables at the top. Variables have to be declared before you get into the begin-end utils to add flag definitions for each field. Then you've got UVM object utils begin and end. And between those, you're going to declare field macros for each of your variables, and you're going to add the field macro flags that you want to use for each of those variables. And so if we've got a transaction class right here, notice I've declared 3 randomizable 8-bit variables. Then I have to declare field macros for each, the most common field macro being UVM field int. That's any number, any vector, any signal is typically UVM field int. And we're going to turn on all the operations. We'll talk about that in a moment. And so I thought, well, I could declare the variables in one line because they're the same size and same type. Can I do that in a field macro? Nope, can't do that. Can't put them all into the same field macro. And I thought, well, obviously the problem is that it can only take one field. So if I concatenate them to get, nope, still doesn't work. And so if you're using field macros, you're going to have a separate field macro for every variable you've declared, even if you could put the variables in single line declarations. And so when it comes to field macros, these are the field macros that you have available to you. You've got UVM field int, and that's the most common one you're going to use. That's all your buses, your bits, your signals. Typically, you're going to declare those to be UVM field int. You could use, those are some of the most common ones for enumerated types, object handles for strings, real numbers, and events. Then if you start doing things like static arrays, there's static array field macros. There are also one-dimensional dynamic array field macros. There's field macros for queues. And if you're also working with associative arrays, then you've got field macros where the first type is the data field type. The second field is the index type for your field macros. And so now you have field macros for string associative arrays, for object handle associative arrays, and for integer number type associative arrays. So there's a large number of field macros there, but usually the only ones, I will back this up a minute, the only ones you typically have to remember are the ones at the top there. Those are the ones that are used most often, with UVM field int being certainly by far the most commonly used field macro. Okay. When it comes to the field macros, after you've declared one of these UVM field int or something like that, you have to include the flags that go with each of the field macros. Of the most common flags is UVM all on. And usually with field macros, what you do is you're saying, all on, and then you start excluding. And so you say all on, except for copy, except for compare, except for this. And so there's no way to say, give me copy, compare. You just have to say all on, then turn off the others. So you can do copy, compare, pack, unpack, record, print, and string print. And the field macro flags that you have UVM all on. And these field macro flags, frequently you put multiples on each field macro that you have declared. And so you're going to OR these together. And we'll show you why it's ORing in just a moment. But you're going to say all on, set all operations on by default. Then you've got UVM default. You're going to use that for default flag settings. And I'll tell you the difference between those on the next slide. Then once you turn everything on, you start excluding what you don't care about. No copy, no compare, no print, no with the red text. We'll tell you about that in a moment. And no pack. There are others that I don't know if I've seen anybody use these. These kind of come from the eSpecman area, where in the eSpecman area you would typically put together policies to say what happens on a physical pin and what happens on just kind of an abstract field. And you can set up policies to use these. I personally have never used these. Maybe someone with an E background might have used these coming into UVM. But it's the ones up top that I typically use. You can also add these together. And most of the time that's safe, but the ORing is actually just a little bit safer, as we're about to see. Okay? Mentor warns about inefficiencies, but users just like the ease of use of these things. Okay? So when it comes to the field macro flags, if you dig deep inside of UVM, you're going to find that there's this one hot vector down inside of it. You don't manipulate this yourself personally, but this is how it's done inside of UVM. There's this one hot vector. And in this one hot vector, if you say UVM default, it turns on all those bits there. Notice that on the pack, record, print, compare, and copy, there's both yes bits and no bits. Okay. And if you say UVM all on, you've set those bits right there. So the only difference being the deep bit. And so bit 16 is the most significant bit. Bit 0 is the least significant bit. What you see there would be the equivalent of saying UVM pack, UVM record, UVM print, compare, and copy, except you don't have those flags. All you have is all on, then you start excluding. And that's why when you say all on, you set certain bits, and then when you start excluding, it sets the no bits in that vector as well. And it's just basically a one hot for each of those functions in that vector. Well, if you look inside the code, you'll find out that that code is commented out. And so UVM default and UVM all on currently do exactly the same thing. This was one of those questions I asked out on the UVM forum. I said, okay, who's using default, who's using all on, and why? And Kathleen Mead, one of the cadence experts, a very respected colleague, came on. She said, well, we use UVM default because we figured if more flags are ever added in the future, that the committee will be smart enough to set the defaults in those flags. And then another respected colleague came on and said, well, we use all on because it turns on everything we want, and we figure if the committee ever adds anything, they'll turn those on. They were saying the same thing. Okay. They were saying the committee will do the right thing by whichever flag we use here. And so the interesting thing is when I look at this, my own personal preference, and it's not a strong preference, you're going to see just about equal numbers of examples out there with default and all on. They're the same thing. I tend to prefer all on. To me, it kind of says, yeah, I'm turning everything on. But you choose whichever one you want. It's going to do the same thing there. Now, before we go to the next slide, notice that most significant bit, the no def print field right there. If you look at the documentation versus version 1.1b, it says the no def print flag does the following, and then the line ends. Doesn't tell you what this flag does. And so this was another question I posted out to the forums. Another good reason for you guys to be on the forums. There are lots of good experts out there answering questions. Guys like Dave59 are out there answering questions all the time. But out there, it basically, the chair of the group came on and says, oh, we'll get that fixed in the next version of the documentation. So their fix was to remove it from the documentation. Okay. I don't know what that flag was supposed to do, but it's no longer documented as of 1.1c. Which is fine. Okay, so when you get to the field macros, you get something like this right here, where we've defined the variables up top. UVM field int, you turn everything all on, and then you start excluding the pieces that you don't want to be available on that field. And so you've got the legal exclusion flags of no copy, no compare, no print, etc., as shown right there. Okay. and the off flags have precedence over the on flags. So on the previous slide, I showed you that one hot vector. I showed you that there's yes and no fields inside of each one of those. So when you do this, when you say all on, they all get set. Then when you turn something off, the no bits also get set inside of that vector. And what happens there is, remember I was kind of alluding to it when I told you about those great big case statements that are put in by the field macros? Because it'll come down and it'll say, is this a copy command? No. Is this a compare command? Yes. Did somebody say no compare? Yes. Abort. Otherwise it'll do the compare operation. And so each one of these actually does a quick check to find out what type of command it is. And then they ask, but did somebody exclude this? And then it aborts the case statement that you find inside a UVM. So the off flags have precedence over the on flags. Also, a few slides ago, I told you that you can OR together the different fields. And now you see why. Because it's a one hot vector, and all you're doing is you're setting different bits inside of that vector. And so you could do something like no copy, all on, and here I've made a mistake, I did no copy again. Well, if I do no copy and no copy, one ORed with a 1 is still a 1. And so if I make that mistake, it's not going to hurt me. Sometimes you'll see examples where people use a plus sign instead of the OR operation. And the plus sign works just fine unless you make the mistake. And then when you add 1 to 1, it goes to 0 and you get a carry. And so you've turned something back off if you're using the plus sign. So that's why we generally recommend that you use the OR symbol. It's just a little bit safer, but of course just don't make a mistake and it doesn't matter. Okay, what about efficiency on these? Okay. So when it comes to efficiency, I've run some benchmarks on this. And the benchmarks I'm going to show you, first let me say what you do and do not do in benchmarking. First, I don't want you to know which simulators I used. I don't want you to know which simulator was which in the benchmarks. I am not trying to prove that one simulator is faster than another. It'd be really silly to take this benchmark and make your purchase decision based off of this one benchmark. If performance is your overriding concern, you try the vendor's tools on your large design with a large UVM test bench. That's a better benchmark than anything I could put up here. When I first started putting this paper together, a good friend of mine said, because I was listing the simulator names, a good friend of mine said, Cliff, you better take the names off. I said, no, I'm not even showing how much time each simulator took. All I'm showing is what is the percentage difference within each simulator. So the vendor should not be concerned. And he said, Cliff, somebody's going to interpret this as meaning this one's better than that, and then the vendors are going to be mad at you. You better take the names off. I took the names off. And so if you want to know how your simulator performs, all this code is in the paper. Just copy and paste it, run the benchmarks on your own. But I'm not going to tell you which simulator. I'm not going to tell you how long the simulations ran, anything. I'll just say that the simulators were all very good and respected simulators, and I like them all. But here, so here what I do is I set up a repeat count, and I keep the count in a separate file. And you'll see that I first tried 10 million, a loop of 10 million, and a loop of 100 million. I try to narrow down these benchmarks to just the things I want to test. If you put a full UVM test bench there, you don't see much difference because the UVM test bench is overwhelming to the benchmark you're trying to run. So I break it down to something really small. And so in a run phase here, I've got this repeat loop that I'm going to actually run 100 million times. And then I have a couple of transactions that have been created. I've got a TR transaction. I've got an X1 transaction. And so in these transactions right here, what I do is I'm going to repeatedly randomize the TR transaction. Then I'm going to copy the TR transaction to the X1 handle. And then I'm going to compare the two. Now, they better compare equal because I just did a copy. Okay? So those are going to compare equal. But I'm going to run this 100 million times to find out about copies and compares and see how those affect the simulation performance. So the other thing that I did in the benchmark, it's always tricky to figure out how to get something reasonable in a benchmark. So how I set it up is, so full disclosure so that you can change the benchmark any way you want. I set up so that the transaction had 5 randomizable inputs and it had 5 outputs. And the question is there a penalty to be paid when I randomize outputs that I'm never going to use the random values? Because once I pass the transaction down to the driver, I'm just going to drive the inputs and throw away the outputs. So is there a penalty for randomizing outputs that I never use? We'll measure that. Then I also implemented the do copy and do compare commands, and I implemented the transactions using the field macros. So the question is there a penalty for using field macros? Because Adam Erickson in his paper said there was a penalty, so I wanted to see if there was a penalty or not. Then do copy with super.do copy, do compare with super.do compare. When you have just a transaction, you don't necessarily need to call do copy and do compare, but when you have an extended transaction, you do want to call those. The question is, should I just get into the habit of calling do copy, do compare, which has kind of been the way I've rolled with a UVM. And so is there a penalty for the unnecessary do copy and do compare that aren't doing anything because they're just calling the ones that are built into the UVM object? And so when it comes to benchmarks, what about unnecessary randomized outputs versus non-randomized outputs using the do methods? And so for one simulator, randomizing those outputs was 16.5% slower. There's 100 million loops through. I always pick something really big. And not only that, I also set it up so that I run each benchmark 5 times in a row. Because sometimes, who knows, maybe somebody's come on and occupied the processor a little bit. I'd like an average of the 5. So about 16.5% slower. Then a little over 11% slower for simulator B, and almost 14% slower for simulator C. Okay, what about randomized outputs if I'm using field macros? What's the penalty? Okay, about 12% slower for simulator A, about 5-6% slower for simulator B, and about 11-12% slower for simulator C. Is there any penalty for using field macros versus the do methods? With simulator A, the field macros were about 6% slower. Simulator B, about 14% slower. Simulator C, about 4% slower. Is there any penalty for calling unnecessary super.do methods? Okay. About 2.5% slower, a little over 3% slower, and about 2% slower. So my takeaway from these benchmarks was, first off, just don't randomize outputs that you're never going to use. All you're doing is paying a penalty for something that you're never going to take advantage of. With field macros, there is a bit of a penalty for using the field macros. And so now you weigh off the ease of use versus the do methods, and you choose which one you prefer to use. But be aware there is at least some penalty for using field macros. And for calling the do methods, the penalty is small enough that I think that the coding style of calling super.do outweighs the small penalty I pay by omitting it. I'd rather be in the habit of always calling the super.dos, but people could change my mind on that one. Okay, so what we have next is some basic transaction objects. And so we've got a transaction that extends UVM sequence item, and I'm going to create a read sequence and a write sequence, and I'm going to create a write read sequence. And we're going to show, because not only is the transaction where you see the 2 different flavors, the other place you see the 2 different flavors is in the execution of the transactions and sequences. And so when it comes to a transaction, here I extend UVM sequence item, UVM object utils, and I have some randomizable fields right there. This was just for a simple RAM device that I was actually trying to show what happens when you're testing something with a bidirectional bus. Then put in a type definition, a little knob there, something that makes my life easier during constraints. I'm going to have an enumerated type, the read-write enumerated type, and I'll declare a randomizable read-write type of the read-write enumerated type. My first constraint is going to say if my read-write type is read, or if it's write, what am I going to set the read-write bit to when I randomize? And finally, standard boring constructor that is part of any transaction. You could add a little bit more, which I will show on the next slide. You can add a convert to string, you can add a post-randomize. Typically, you will not add a post-randomize as I've done here. I just wanted to see some activity happening. But we will create from the UVM sequence item our transactions. So next, I've added the convert to string where I show what all the fields are so I can call this at any time. And then I've got a post-randomize. Post-randomize is just going to print out that a transaction has happened, and I'll say this.convert to string. It has been pointed out to me that I really didn't need the this keyword here. I could have just called convert to string, and it would have called and shown me my transaction, and a verbosity of high, because I don't want this to come out by default. I want to turn up the verbosity if I want to see those transactions. Okay. So in a read sequence, you extend the UVM sequence, and you parameterize to the transaction type you're interested in. You register it with a factory with object utils, put in the same 3 boring lines of constructor code that goes inside of any transaction type, and your sequences must have the body task. And so inside of that body task, and that, by the way, is something else you never call. All you're doing is saying when the sequence is executed, it will run the body of my sequence. And so inside of the sequence, we've declared a transaction handle. We've factory created the transaction, and then we're starting communication with the sequencer, and then we're randomizing with the read-write type equal to read, because this is a read sequence, so inline constraint, and then finish item. And so when you see start item, finish item with transactions, you're looking at more the Verification Academy style, where you're saying start item, finish item, and you're executing the code explicitly. In a few slides, we'll show more of the macro style. So this is the second place where you have two different flavors. Then in the write sequence, you extend UVM sequence, and have the transaction type, register it with a factory, put in the same boring constructor code, and in your body task, once again, declare a transaction handle, factory create it, start communication with your sequencer, randomize with an inline constraint saying you want the read-write type to be write, and then finish communication with the sequencer. Now, if you're going to run a sequence of sequences, then using the method style here, it's just a little bit different. So using the method style, we're going to create a write-read sequence that extends UVM sequence, and it's going to still use the same transaction type, and we're going to register it with the object utils. In this particular sequence, I'm adding a randomizable count constraint that I want to be able to execute this 3 to 5 times when randomized. Put in the same boring constructor, and then in the body task, we declare handles of the 2 subsequences, and we factory create those. And then we're going into our repeat loop with the count that I'm going to randomize. And here's where things are just a little bit different. Instead of start item, finish item, you now say sequence.start. Now, what I'm showing up there would probably make Justin cringe. I think last year he cringed when he asked how many people are using the mSequencer handle. And you're not really supposed to use that. You're supposed to use the getSequencer static method that will return the mSequencer handle. But most of us found the mSequencer handle, and we've been using it. You probably should do it the other way, but I'm going to show it right here. Every single sequence, whenever you start a sequence, you are going to start a sequence on a sequencer. And when you start a sequence on a sequencer, what you've done, every single sequence has inherited from UVM sequence an mSequencer handle. That handle gets set. And so now every sequence has a handle that says, that's the sequencer that I'm running on. Okay, I was started on that sequencer, and so the mSequencer handle, that's the handle of the sequencer I'm running on. And since we're going to run sequences of sequences, what we want to do is we want to start those sequences on the same sequencer that this sequence is running on. And so a pretty common technique is just say sequence.start on the same mSequencer, which happens to be the handle that this sequence is running on. So they're all running on the same sequencer. Same thing right there. Again, the more proper way would have been to say getSequencer. And with the UVM do macros, as we've already seen, you can execute UVM do, and the difference with UVM do macros is that it can figure out whether you're running a transaction or a sequence. So it does a quick little test inside of the macro to figure out which one you're working with. And so it'll run either a transaction or sequence. You don't have to know 2 styles in order to execute it. And it'll do the create, the start item, randomize, and finish item, each of those commands. And if you're saying do on, frequently you do this with virtual sequencers, where you'll say, I want this sequence to run on that subsequencer, this one to run on that subsequencer over there. And then you can do it with certain priorities as well, as we saw on an earlier slide. And you can do the inline constraints. And I showed you that I was doing a read sequence and a write sequence by setting the read-write bit during randomization. Okay. Again, those are commonly used on virtual sequencers, less commonly used but available to you. Okay. So if you're doing the do methods, the rule is you're going to use UVM object utils. Typically, you don't use begin and end. You just UVM object utils. You've got field macros to declare the transaction variables before calling the field macros. That's a field macro rule. And you declare the variables before registering the transaction with the factory. Then, with field macros, you must use object utils begin and end, and you're going to put those field definitions between the begin and end if you're using the field macro style. Both of them work just fine. Now you know why when you look at examples out there, they don't always look the same. Some are using more of the field macro style and the UVM do's. Others are using more of the do methods and the built-in methods as well. So do not directly override the standard transaction methods, such as copy and compare. I mean, come on, get a life. You really don't need to do that. That's going to consume a large portion of your life if you try. Never manually implement the create method. Just use the UVM object utils macro to create that for you. Transactions should include a convert to string. Whoever's coding up the transaction, it's a common courtesy to anyone else on the team to add a convert to string. That way, anybody else on the team can very easily call the built-in convert to string to print out, well, so what are the current contents of this transaction? Without a convert to string, they're going to be calling print or something like that consumes quite a bit of space, quite a bit of processing. They work just fine, but you're going to get these nice tabular outputs or tree outputs when you call these, and they do take quite a bit of time to actually execute. If you must use one of them, at least use the string print one, because that one can be used with UVM infos and put under verbosity control so that you can turn them off if you don't want them on there. So it can be called from the messaging macros. Better yet, use the convert to string. It's a nice format, a very succinct format that can be called and used when running the simulations. All right, so let's continue. This next one right here is actually quite important and is frequently done wrong. I have an entire paper on my webpage dedicated to this topic. I mean, who writes a paper about, the messaging is basically the UVM $display command. Who writes a paper on a $display command? Here I am, okay. But you're going to see why we talk about this in this section here. So by way of introduction, why did I even write that messages paper? Okay. First off, verbosity settings are not message priority settings. And that seems to be the biggest confusion out there. Verbosity does not equal message priority. As a matter of fact, verbosity is roughly equivalent to the opposite of message priority. UVM low is not a low priority message. UVM low is one of the highest priority messages. References and public examples get it wrong. The user guide, the class reference, 2 recent UVM books, all get it wrong. That's why we wrote a paper about the UVM $display command. The paper offers guidelines on proper usage. It shows some useful messaging tricks. I'll show you one of the tricks. You can get more tricks out of the paper itself. So first off, the Verilog $display command. Thank you, Verilog $display command. You have served us well in your lifetime, but we are now done with you. Okay? We are now done using the $display command. You have messages and messaging macros. And by the way, this is one of those places where all vendors agree you want to use the macros, not the message methods. So everybody agrees to use the macros. UVM low should almost never be used in your macros. It's widely misused in books and examples. Convert to string, you should override the convert to string because this is where you would put what you would normally put in a $display type command. It's basically a built-in show my contents method. So when it comes to message type facilities, one of the places where I went to and learned quite a bit about the topic was the book by Sharon Rosenberg and Kathleen Mead. They had a good discussion of this topic. The $display command does not allow for easy message filtering. Most of us who have used display and test benches, we all know about the if-def debug that you put around your display messages. So you recompile when you want to see a message, you recompile when you want to turn it back off. The UVM report info, warning, error, and fatal methods allow message filtering. And so again, these are the methods, not the macros. You can filter by their ID. You can filter by their verbosity setting as well. And then there's the macros that everybody agrees this is what we should be using. When it comes to the macros, they further simplify the usage of each of these methods. So you have UVM info, UVM warning, UVM error, and UVM fatal. These automatically include the file name and line number, which are useful for debugging. There's a way to turn it off, and we'll show you that as well. And they're more simulation efficient than any of the methods shown above. So if you're using one of the method varieties, one of the messages, and by the way, when you look at examples, certainly the older UVM examples tend to use the methods. Once you get to newer ones, they tend to use the macros. But the methods have reporting services built in for all your components. And the methods, the UVM messaging methods, take up to 5 different arguments. The last 3 have default values. So you put in a short string ID, and that shows up in your reports, and it allows you to easily filter. You've got the string message, what you would have put into the $display command. That's what you put right there. And then a verbosity level. By default, the verbosities are shown up there. By the way, once you get into the IEEE UVM, I'm pretty sure that I saw in the DVCon 2017, 2018 presentations, I believe UVM report error now changes to UVM none, so it doesn't turn off. And I think UVM report warning, I think the verbosity changes to UVM low, so it comes out very frequently. But otherwise, these are the verbosities that are currently being used. The methods themselves have a file name string argument, and it's an empty file name currently, and so it doesn't print out anything, and it also has a line number equal to 0, so it does not print out the line number unless you add that in. And so you just say UVM report info, just a little ID string of run, and what the message is, and turn the verbosity onto UVM high. If you're using the macros, they are more efficient than the simulation messages, the methods from the previous slide. Even though they call those methods, they are more simulation efficient. Now, how does that work? We'll show you. The macros take 2 to 3 arguments depending on the macro type. Again, you add in the simple string ID, you add in the string message just like you would in the $display, and then you put in a verbosity, but only if you're using UVM info. The other macros all have a default verbosity of UVM none that you cannot change. That's actually one of the things that I would like to see change going forward. I'll mention that later. The macros automatically include the file name and line number for you, so you don't have to get that added in when you use these. And so you can say UVM info, again, the environment is still running with a verbosity of UVM high. And so all of your messaging macros are more simulation efficient than the methods that they call. How is that? Well, because the macros wrap those message calls in these if statements that basically check the verbosity before doing the string processing. You see, the methods, they'll do the string processing whether it's coming out or not. But the macros do a quick check to find out, is this even coming out? If not, let's not do the expensive string processing. And so they're more simulation efficient. So it removes that expensive string processing. They also include these macros that we added to the 2009 System Verilog standard. These macros were the _file, _line. And so this will help you to report what file is printing this and what line number it is coming from. If you think that that's a little too verbose, then during compilation, you just need to turn on this switch here. You just define UVM report, disable file line, and those will get turned off so it doesn't take up so much space when these are reporting. But UVM warning, UVM error, UVM fatal include the predefined default UVM verbosity setting, and it happens to be UVM none. So convert to string. The built-in convert to string that you get in UVM object returns an empty string. So you're always intended to override the convert to string. It's user definable. So it's a virtual function. It's a user definable hook. It's called directly by the user, so it's very simple to use. And users provide object info in the form of a string. And so in the convert to string, it's going to return a string that is often used in a UVM info command. There's no printer policy required, unlike string print, and the format is fully user customizable, which is what you're used to in $display. You can put in whatever formatting you want. So if you'd like to print out these transactions, if you use the built-in print, it's going to print out typically this table with lots of string processing, whereas if you call your convert to string, you can put it out on just a few lines. It doesn't take too much space, doesn't take too much time either. Convert to string should be added to all your transactions. So this one's a fun one. $S format, $S format F, and $PS printf. And I even have my sources for this information sitting in the audience. And so I know I'm going to be checked on this one. So with the $S format F, this is part of the IEEE 2001 standard. It's used to generate a formatted string. And so it's a standalone command. You say $S format, which means the first argument has to be a string variable that the string will be assigned to. Then you put in your formatted string and list of arguments, much like you would with the $display command. Then there's the $S format F. It's just like $S format, except it returns a string. It's a format function, so it just returns a string. And so you don't have a first string variable argument in the command itself. And so you'll have some string variable equals $S format F, or you'll call the UVM info, and the string you want comes from a $S format F command. And so you've got the formatted string with all the formatting that you would typically do inside of $display. Then we've got $PSPrintf. This one is kind of funny. And I'd like to thank my good friend Chris Spear. It's only in the past year that I learned the backstory behind this one. Chris is a smart guy. He's written a really good system Verilog verification book. He's the one that gave me the information on this one. The $PSPrintf, and by the way, there's lots of people that have these confused. It's exactly the same thing as $SFormatF. As a matter of fact, I've got some very good contract consultant friends that have gone on to forums and said, well, I think the SFormatF or the PSPrintf is a little more simulation efficient than the other. They're the same thing. They are exactly the same thing. The backstory behind this is that Synopsys acquired Vera. And Chris worked for Vera, a very good verification language, which was a foundation for much of the verification language in System Verilog. And so in Vera, they had customers that had requested for the Vera language that somebody implement. Okay, first off, you look at that name. I mean, is it PSPrintf? What is that, kind of like PostScript printf or print string print? What's the PS for? Okay, now we're going to tell you because Chris told me. The PSPrintf, they were requested at Vera to provide a Perl string print function. PSPrintf, Perl string print function. It's like, that's a bit of a letdown, you know. I mean, what's the meaning of this? It's the Perl string print function. And so Synopsys had implemented this a long time ago, and then the IEEE standard comes along and we standardize SFormat and SFormatF. Well, this is back in the days on the System Verilog committee where everybody who attended the committee meeting had their own vote. Now it's by company. It's called entity-based voting. But back then, anyone who was a member in good standing would vote on any of the proposals for the standard. Back at that time, the proposal came in from Synopsys that we would like to add the $PSPrintf to the standard. It'll be exactly the same thing as $SPrintf, but we've already implemented this. Our customers are using it. Can we add this to the standard? And I had to go back and look at the voting to see how I voted on this thing and how everyone else voted. And so back in that time, the proposal came out, and everybody from Synopsys voted, yay, we should add this to the standard. Everyone from Cadence and Mentor voted nay, we should not add it to the standard. And all of us users, I looked it up, we all abstained. We knew that this was a fight between vendors and we wanted no part of it. so PSPrintf is not part of the IEEE standard. As a matter of fact, just last week I decided, I wonder if it's in the 2017 standard yet. Did a quick check, not there. PSPrintf is not part of the System Verilog standard, but it appears all the vendors have implemented it. And again, I went out to the forum, I asked the question, I thought we said that this would not be part of the standard. And one of the vendors came on and said, yeah, but customers were using it, so we had to implement it. And what does it take to implement it? It's the same command they already had. And so they just had to make either command work. The problem with having a $SFormatF and a $PSPrintf is that these show up kind of equally out in examples out there. You're going to find SFormatF over here, PSPrintf over here. And so anyone who's new to UVM, you get into this thing and you say, I wonder why they had to use the PSPrintf function this time and the SFormatF function that time. And there is no reason. Okay? You can use either one liberally and freely. It doesn't matter. Unfortunately, you get into the user guide, and some of the examples have SFormatF and some have PSPrintf, which just further reinforces that, oh, these must be different commands. It would be better in the user guide and in the reference manual if all the examples would be converted to SFormatF, just because they can find the documentation for that in the IEEE standard. But now you know the backstory, and now you know no difference. If you're using one, if you're using the other, you're going to get the exact same results. There's no simulation performance penalty for one over the other. But again, when you're new to this, you're looking at the examples and saying, I wonder why it's this one this time. And now you know it's a silly reason. Okay, what about verbosity? What does verbosity mean? Well, highly verbose simulations would show lots of messages. Minimally verbose simulations would only show a few important messages. And UVM has a built-in verbosity enumerated type, and it is defined as follows. And so if you ask for a UVM verbosity none, that's an integer value of 0. And that'll print all the time. You typically just don't have a way of overriding that. You can, but not from the command line. If you put in a verbosity, by the way, the reason you like these verbosities, look at these commands I'm putting up there. You put your favorite simulation command there, whether it be vsim, whether it be simv, whether it be xrun, your favorite simulation command, you put on a verbosity and it does not recompile your design. And that's one of the advantages of these verbosities, is you can say, okay, turn up the number of messages, I need to see more debug. Okay, now turn it back down, and you're not recompiling each time in between. That's why these verbosities are so important. Whereas the $display, it's going to be inside of an if-def debug, you're going to have to recompile to turn on or turn off these messages. So UVM low has an integer value of 100, and so you print if the selected verbosity is UVM low or lower. If UVM medium has a verbosity level of 200, you print if it's medium or lower. Then you've got UVM high, which is level 300. You've got UVM full, which is level 400. And you've got UVM debug, which is level 500. I know someone has said, we were never supposed to find UVM debug. Okay. That wasn't for us. That was for the library developers. But most of us who've been out and tried to learn this thing, we got into the source code and we found something that said debug. And so we've been using UVM debug all the time. But that was really meant for the library developers. I'll have more to say about that in just a couple slides. And so if you want to run with low verbosity with showing just the important messages, then your important messages should have been given a verbosity of UVM none or UVM low, and those will be printed out. But if you want to print out more messages, then you might turn up to high or higher, and all of those verbosities are going to be printed out. And so with the UVM verbosity, you've got level 500, which is debug, 400 is full, 300 is high, medium is 200, low is 100, none is 0. When you ask for debug, any message is going to be printed when you call for it without recompiling. When you ask for medium, it's only level 200 or below that's going to be printed. Medium is your default. You don't have to put medium on the command line. Those messages are coming out automatically for you. And there's two ways to change it. You can do it from the simulation command, not the compile command. You've already compiled. Now you just resimulate with a different setting for a different verbosity, or you could put it into your test code yourself if you'd like to. So a little useful debugging trick here. I like the technique where I can see my test bench and factory setup before I go into the run phase. Because if something goes wrong, it's usually during the run phase. And so I'd like to have a printout of what my test bench structure looks like and what is currently inside of my factory. So I have a test base class that extends UVM test, and I have the start of simulation phase in there. Remember, you've got build, connect, end of elaboration, start of simulation. And so most of the important work is during build and connect, end of elaboration, some final settings that you might want to put in there. Start of simulation, I think of that as being my pre-run phase. Is there anything I want to do before I ever start running the simulation? I stick it in start of simulation. And this is what I put there. I'll say that I'd like to say this.print. I'd like to print out what my current test bench structure is, and I'd like to do a factory.print. What do I have currently stored inside of that factory? The problem is those printouts are unconditional. They're not under verbosity control. I could use an sprint for the this, and so then I could put that under verbosity control, but there was no sprint for the factory, so that's coming out automatically. So what I like to do instead, one of the tricks you'll find in the paper, there's a few of them, is I actually want to view the test bench and factory setup still in the start of simulation phase, but I can check the verbosity level that is on the command line. I can say, only if someone has asked for UVM high or higher do I want to print these out. And so if I say UVM high, then I can print out what my current test bench structure is, and I can print out what my current factory contents are. So now it's under verbosity control. And so if I turn up the verbosity, I can see this, but by default, I'm not going to show this coming out. It allows conditional printing of the test bench and factory setup. So documentation errors. When it comes to UVM low, it is pervasive throughout examples that you'll find in industry. In the UVM user guide, you've got the $display command used once. It's like, aren't we trying to get people away from $display? But it's there once in the user guide. Then 3 of the macro examples have bugs in them. 5 of the examples use UVM low, which is the wrong verbosity. And 2 of the macros do not use UVM low. Those are correct. So out of 11 examples in your user guide, in my opinion, 9 of them are wrong. Then you go to the class reference, where one of the macros has a bug in it. Then 3 of the macros use UVM low, which is the wrong verbosity. and 2 of the macros use a verbosity other than UVM low, and those are correct. So out of 6 examples, 4 of those, in my opinion, are not correct. It's no wonder the books and papers are getting it wrong, because the user guide and the class reference are just full of bad examples of using this. And then there was a popular book published in 2013 where more than 20 examples use UVM low. That is wrong. Another popular book in 2013 is more than 30 examples using UVM low. It's wrong. And so users are out there using UVM low all over the place inside of their code. It's the wrong verbosity. So let's give you what I call my guidelines for using the different verbosities and the different macros. I'll use UVM fatal for any test aborting errors. I'll use UVM error for non-aborting simulation errors. I'll use UVM warning to warn someone that I'm about to do error injection on this model. And UVM none for final reports. And so those are not filtered by verbosity settings. All of those are basically non-maskable. You can still play with them down inside of the code, but just by default, you don't see any of those being changed. The UVM warning I use very sparingly, because I think it is implemented wrong. UVM warning has a built-in default verbosity of UVM none, so there's no way to turn off warnings once you use it. I think that's wrong. I've submitted this to the UVM committee. I'm not sure what its status is, where I would like to see UVM warning changed in the future so it takes a default verbosity of UVM none. What that means is no existing code would have to change. It would behave exactly the same way it does now. But now I could apply a different verbosity setting to my warnings so I could get warnings to turn off. I currently do not use UVM warning because I just can't make them shut up during my simulation. Then you use UVM low for high priority messages. And so that is almost always on. And UVM medium, I use that if you're confused about what you should use, think of UVM medium with the UVM info macro as your new $display command. Because by default, that is coming out, but you can turn up the verbosity and get those turned off. And so the UVM info with the UVM medium verbosity is your new $display command. Use that to replace any existing $displays that you have in your code. All of those above messages print by default because UVM medium or higher, or I should say lower in the integer values, those all print by default without you putting a verbosity setting on the command line. Beyond that, then you get down to UVM info with a verbosity of UVM high. I use that in 2 places. Showed you a couple slides ago where I use UVM high to say, do I want to print out my test bench structure? Do I want to print out what's currently in the factory? So I use that there, and I also put it on all my transaction passing messages. Because when you're first doing debugging on a design, you frequently don't want to just see the errors. You want to see what is actually running to see if it makes sense. And so whenever we do labs, we tell people the first runs, turn up the verbosity to high, so you see the errors and the passing messages. Then after you're satisfied that it's working, you can go back to a default verbosity or turn the verbosity low, and now you're not going to see the passing messages anymore. UVM full, I use that to print status messages. So if you want to say something like, I'm now done with the connect phase, I'm now done with the end of elaboration phase, you could use that so that it rarely comes out. And UVM debug when you add debug type messages. Okay. All right, so let me tell you what I would change about this in UVM. I've already told you about warning. The UVM warning macro should have a default verbosity of UVM none, so no existing code changes, but we have control over it. Second thing I would do is that UVM full and UVM debug, again, UVM debug was never intended for us, but we all found it, and we've all been using it. That was meant for the library developers. So whenever you turn on full or debug, not only do you see your messages, you see a boatload of messages that come out of the library. I would like to see us add 2 new verbosity levels, level 600 and level 700, that would be UVM live info and UVM live debug. And then document them. In the documentation say, these exist, but they are intended only for the library developers. Do not use them. This is for library development. And then we'd ask the library developers to get out of our space. Take all those messages that are currently showing up in UVM full and UVM debug, put them down in UVM live info or UVM live debug so that that's our space right there, not their space. That's what I would change. The other one that I would also change is UVM info. UVM info is the only one of those macros that requires a verbosity setting. So you use UVM error, you've got a default. UVM warning, you've got a default. UVM fatal, you've got a default. UVM info, you don't have a default. How many times have I had syntax errors because I forgot to put a verbosity on my UVM info? I'd like to have UVM info to have a default verbosity of UVM medium so that I don't have to set it and I can print things out, but at least I can change it. So those are the three things I'd want. I'd want to see UVM warning, have a default of UVM none, but I can change it. UVM info, have a default of UVM medium, so I don't have to add it if I don't want to. And I'd like to see a UVM lib info and a UVM lib debug levels 600 and 700 and get out of our space. Use that for the library developers. Document it, tell the users they should not use it. They never told us about UVM debug, so we all found it and we all used it. Okay, so now let's talk a little bit about analysis ports and analysis paths. And this is actually based off of a paper that Heath Chambers and I did this past year. So he's my co-author on this, a lot of good stuff in there. We're going to talk about basic queues, mailboxes, and TLM FIFOs, our first pass. We're going to compare this to subscriber satellite TV. We'll talk about analysis paths, analysis ports, exports, and implementation ports. We'll talk about TLM FIFOs, more detail. We'll talk about the importance of that copy method in these analysis paths and how analysis ports connections work with the write method. And finally, a summary and conclusions. And again, there's a paper on the webpage that has all the details on this. And so the paper has more than what we're going to have time to talk about in this section right here. So first, I want you to pay attention. We have queues inside of System Verilog, and these are great to store component handles. We also have mailboxes, and these are great to store transaction handles. Okay. So let's talk about those. The queues, we can store component type handles. And so there's a pushback method for your queues to say, just take this handle and push it onto the queue. There's a for each method, so we can walk through all the handles currently stored inside of that queue. But the problem with queues, why they're not typically as valuable in a scoreboard, is they don't have a blocking get method. So they've got methods to pull things off, but you have to kind of pull or use other status techniques to find out if there's anything there that you can use. The mailboxes, on the other hand, are great to store transactions. They do have a non-blocking try-put method to put something in. That's going to become very important to us for analysis paths. And they do have a blocking get method. The blocking get method means that once you call a get on this mailbox, it waits until there's something there for you to retrieve. So you don't have to keep polling to find out, is there anything there yet? Instead, I'll just say, give me something that's there, but wait until there's something there to get. And so these are great for scoreboards. We're going to talk about analysis path considerations. Your analysis paths start with an analysis port, and they must, each analysis path must terminate with an analysis implementation port. And then you've got your UVM TLM FIFOs and UVM TLM analysis FIFOs. These are built using System Verilog mailboxes. The code inside of these, if you want to see some UVM that actually is pretty understandable, look at the code inside of these, because this isn't too hard to understand. The UVM TLM FIFO cannot terminate an analysis path itself, whereas the UVM TLM analysis FIFO can terminate an analysis path, and so they become very valuable inside of a scoreboard. So let's talk about subscriber TV just 1 minute, satellite TV. There's two ways to watch a broadcast television program on subscriber TV. Your choices are you watch it live, or you turn on your DVR to record the program so you can come back and watch it later. Satellite programs are broadcast as scheduled. It doesn't matter if there's thousands of viewers out there or if there are no viewers, that program is coming from the satellite as scheduled. There's no way to restart a broadcast program. So there's no way to come in and you say, oh shoot, I'm 15 minutes late, I want to see this program from the beginning. I'll tell the satellite to start over again. Okay? There's no way to tell the satellite to start over again. But even if there was a way to do that, the other people who are watching the program live would be pretty upset that the program started again because you were 15 minutes late. You either need to watch it live or you need to record it. And subscribers are not allowed to change a live program. You're not allowed to mess with the program that is coming from the satellite. If you have the right equipment, you can take a copy and then maybe you edit it for language and content, your own copy, but you cannot modify the one that is being broadcast. This largely describes what happens with analysis ports and analysis paths. And so analysis port connections, we'll talk about that, and TLM FIFOs. So first, after the monitor has sampled signals from the DUT, it reassembles a transaction. So the monitor has sampled all the signals, reassembled a transaction, and now it needs to be broadcast to the rest of the UVM test bench. And so there's an analysis port, which is a broadcast port on your monitor, and it just sends the transaction. It has gathered up the signals for a transaction, and it broadcasts the transaction handle out to any device that happens to be a subscriber, any device that happens to be watching. And so the common paths that you'll find inside of analysis paths where there are multiple subscribers is frequently in your UVM, you've got your monitor with an analysis port on it, the broadcast source. And then it frequently is connected to an analysis port on the agent, which is really little more than a transfer station. It's a way of copying handles. And then this frequently goes up to a coverage collector, which is frequently an extension of UVM subscriber, so it has an analysis implementation. So in these diagrams, you're going to see the little purple bubbles represent the implementation termination point. You usually don't see these as blue and purple, but I'm going to do it in these slides right here. And so that's the termination point. That's the first path from the broadcast transaction. The second path frequently comes into an analysis export on the scoreboard, which again is little more than a transfer point. And then it ends up at the implementation port of the scoreboard predictor. And that is frequently an extension of UVM subscriber with the implementation port on it. Then yet another path is the broadcast transaction heads over to a comparator's analysis export, again, a little more than a transfer station, and then ends up at the input of a TLM analysis FIFO. The TLM analysis FIFOs are really nice because they help to terminate those analysis paths. So that's the third termination point. So in this example, we had one broadcast port and 3 termination implementations, or subscribers. Also, in that scoreboard, frequently we will put another analysis port on the predictor, and so we'll get the transaction in, calculate what the expected value is, then we will broadcast the expected transaction also over to the comparator. So it'll first end up at an analysis export on the comparator, a little more than a transfer station, and finally it terminates at a UVM TLM analysis FIFO that has the implementation port built into it. And so the second path there is just one broadcast source and one termination implementation point. So legal paths, when you're looking at analysis ports, what are the legal paths? Well, first off, you can start off with just an analysis port connected to nothing. I mean, you can have a satellite up there that's broadcasting a program that nobody ever watches, but it's still going to broadcast. So it's okay to have an analysis port that isn't connected to anything. And so you could be broadcasting out into the air. Or you could have just one termination implementation point on the path. And wherever you have an analysis implementation port, you're required to implement the write method. Basically, the write method is there to say, what am I going to do with the transaction that has been broadcast? So once the transaction comes in, what am I going to do with that transaction? Something a little more complex, you've got an analysis port that is a broadcast source, and then that's going to go over to another analysis path on another component connected there. It might connect to yet another analysis path on another component right there. And then finally, it's going to go over and start connecting to analysis exports. And again, all these ports in between are just copying handles. They're just transfer points. And that could show up at another analysis export on another component inside of that component. And finally, it shows up at an analysis implementation port on another component, and that terminates the path. And wherever you've got an analysis implementation port, you must provide a write method. The write method, again, says, what are we going to do with this broadcast transaction now that it has reached the final point? Illegal paths for analysis ports. You could have an analysis port and you could tie it to an analysis export, not an implementation port, but an analysis export, which should only be a transfer point. Even if I implement a write method inside of that export, you get error messages. How do I know? I've tried. Okay. Yeah, I implemented the write method and it basically says that this is not going to work. And so even if you've got a write method inside of an export, it's not going to terminate that path. Similarly, you might have an analysis port that goes to an analysis export. That part right there is fine. You can always have an analysis port that talks to an export, but then if that export tries to talk to another analysis port, that's going to be an error. And so the compiler is going to give you errors that you're not allowed to do that. And so the second analysis port, it would be fine if it were coming from an analysis port, but because it's downstream from an export, that's what makes that an error. And then it finally shows up at an implementation, and so far so good. We put in the right method to terminate that path, but then if you try to connect anything beyond that point, that is an error. And once you get to an implementation, that is the end of the path. There are no further connections that are made beyond that point there. And not only that, but we're terminating again with an export, which you can't do. You'd have to have an implementation there. So when it comes to analysis ports, right now recommended usage would be if you've got an analysis port with an arrow going out to another analysis port to another analysis port. Basically, if you've got arrows leaving your components, you're talking about connecting analysis ports, even though most of those are just passing the handle along up to the top. Similarly, on the receiving side, you might have an analysis export that then goes to another analysis export and finally ends up at an analysis implementation port. And there you must have the right method implemented. And so when you see arrows coming in, typically you should be thinking about analysis exports or a final analysis implementation to terminate the path. And so here, let's look at a typical example from a UVM scoreboard. Here I've got a monitor that has an analysis port, and I connect it to the agent's analysis port. And then that is connected off to the input of the test bench coverage collector that has an implementation port. Now, frequently we implement the coverage collectors by extending UVM subscriber. UVM subscriber already has a built-in analysis implementation port. By an unfortunate naming convention, it happens to be called analysis export. But it is an implementation port to terminate the path. And then we have an analysis export going to the wrapper scoreboard, and then that is then broadcast up to a predictor that, again, we typically extend from UVM subscriber. And so from UVM subscriber, once again, we are given an analysis implementation port to terminate that path, and we're required to provide the write function. By the way, the write function is also required inside of the coverage collector because these are the termination points. So we have a write method to terminate that path right there. And then in the predictor, we frequently also declare yet another analysis port because after we take in the transaction and predict what the output should be, we broadcast that over to the comparator. And so we put an analysis port on our predictor. And then on our comparator, we've got a couple of analysis exports. And so the analysis export on the scoreboard wrapper itself is connected to an analysis export on the comparator. And also, you've got the analysis port on the predictor connecting to an export on the comparator. And then inside, just inside, we stick two of those TLM analysis FIFOs. And that's the style that Heath and I usually prefer when we're putting together these block-level test benches. And so the TLM analysis FIFOs already have the implementation port built in. And so the implementation port for each one of those is going to terminate those analysis paths. Again, unfortunately, they are implementation ports, but the name used for those ports is analysis export, even though it is an implementation port. And then they also already have the write methods built in. So when a transaction is broadcast and when it makes it up to a TLM analysis FIFO, it takes the transaction and it puts it onto the mailbox inside of those TLM FIFOs, which means you don't have to implement those write methods. These are your termination points, and it has implemented the right methods for you. Then inside the comparator, frequently you set up a run phase with a forever loop that's just going about saying expected FIFO get or output FIFO get. So it's going to extract both of those, and these are blocking gets, so they wait until there's one in each one of those, so you don't have to do any polling, you don't have to keep track of if you've read too many from one and not the other, and then you do the comparison. So TLM FIFOs, a little bit of definition and usage here. Scoreboards typically store expected and actual transactions. So they take the inputs, calculate the expected, and the actual transaction. They need to run the comparison between those. System Verilog has queues and mailboxes built into the language. And so you've got a queue example there, you've got a mailbox example. And then, which one should be used, though, inside of your scoreboards? Well, let's recognize what they do. With your queues, there's a push front method, so you can push a transaction onto a queue, and there's a pop back method to pop a transaction off of the queue. And on the mailbox, you have a try put command, which basically is a push command that returns status, whether it was successful or not, and it has a try get command to pull something off the back and again returning status whether it was successful or not. These are all non-blocking functions. They must complete in 0 time. And so if there isn't anything there, you're not going to get what you wanted when you try to do a get operation. The mailboxes, on the other hand, have a blocking put command. So you can say if my mailbox is full, depending on how you've defined it, I want to put another transaction in, but wait right here until I succeed in putting the transaction into the mailbox. And it has a blocking get method as well. The blocking get method says on the other side, I'd like to get a transaction out, but if there's nothing in here right now, then wait until something's there and then I will grab it. And so those are both blocking tasks that are on the mailboxes. The pop back is not exceptionally useful inside of a scoreboard because you don't really have a way of waiting until something's there. And so you might go into some polling or check frequent status. Is the size greater than 0 before you actually call that command? And so queues are kind of hard to use in a scoreboard. I have done it in the past, but mailboxes are the way I've gone now. On the other hand, I cannot call a blocking put command from a function. And remember, we said that on your analysis implementation ports, they require a write function. And so it's the write function that it needs to call something, and it cannot call a blocking put. A blocking put would consume time, so that becomes illegal. So we typically do not use that, but the blocking get we do use inside of our scoreboards. Because there we can set up the forever loop that says, get one of these, wait till it's there, grab it, get one of these others, and now let's run the comparisons and let's keep looping. And so I don't have to have any type of timing controls inside of my forever loop, inside of the scoreboard. I just say get one or get the other. On the other hand, the try put command becomes very important for pushing something onto a mailbox, because the try put command is a function that completes in 0 time. That is something that can be called from the write function. And what we're going to do is we're just going to make sure that mailbox is always unbounded so that we can always put in something else in there. We don't have to wait. We don't have to check the status. And there is also a try put command to get something off the back end, but that's just about as useful as the pop back command on the queue. And so we typically don't use it because it doesn't wait till there's a transaction there to be retrieved. Okay. These mailboxes are used by your TLM FIFOs. And so when you get into the TLM FIFO, you've got the TLM FIFO base, then TLM FIFO, and TLM analysis FIFO. And the TLM FIFO already has 4 ports built into that TLM FIFO, and typically we don't use any of them. They're there, but we typically don't use them. Instead, what we'll frequently do is, first off, with the TLM FIFOs, by default, they're only 1 location deep. And so when we create them with an additional argument, a 0, to say this is an unbounded TLM FIFO. Then we use the try put method to store transactions into the mailbox. And the try put will always succeed, but we need the try put because we had an analysis implementation port that required a write command, and the write command needs to push something onto the mailbox or the TLM FIFO, and it's going to use the try put command, which will always succeed because it's unbounded. And then what we do is we typically void cast the try put command. That is, because try put returns a status saying whether it succeeded or not. We frequently just throw away that status. We expect to always succeed. On the far side, you've got the blocking get method on these TLM FIFOs. So you can get a transaction from the mailbox, and it is a blocking get. Wait until you succeed in doing so. And so the scoreboard comparator will call the get on the expected and the actual outputs, and then run a comparison between those. So that's your TLM FIFO. Your TLM analysis FIFO is the one that we prefer to use. It's an extension of the TLM FIFO. And so you have the same 4 ports that we had on the TLM FIFO that we typically don't use, but it does have an analysis implementation port on the TLM analysis FIFO, and that is one that we will use. Your UVM TLM analysis FIFOs by default are unbounded. You don't have to say 0 for the TLM analysis FIFOs. They are already unbounded for you. And so it terminates an analysis path for you, which is very convenient. It has an analysis implementation handle that is, again, unfortunately called analysis export, but that's the handle on the TLM analysis FIFO. And the implementation has the write method already built in. The write method, when the write method is called, it does this.tryput with a void cast, so it does the pushing of the transaction into the mailbox for you. Very nice, very convenient. It still has the block and get method, just like the TLM FIFO, which we want to take advantage of inside of our scoreboards, because we'll use that as a block and get to get the expected and to get the output transactions. Okay, so let's look at a couple of typical TLM scoreboards. The first one here is one that you often see in examples. Keith and I actually don't really like this one much, but it has a couple of interesting features to it that are worth sharing. So you've got an analysis port on the monitor, an analysis port on the agent, and then you might have two analysis implementation ports on your scoreboard. This is what you see in some examples that you'll find out online. Now remember, analysis implementation ports require a write function. But you're only allowed to have one function called write inside of any component. And so we're in a bit of trouble here. We have two implementation ports. Each one requires a write function. Well, all the vendors agree that this is a good macro. The UVM analysis implementation declaration macro, where you're going to say, I want to create two new implementation ports with this suffix and two write methods also with that suffix. And I'm not going to explain it here, but go into the paper and it explains how that macro works in order to build the two implementation ports and to build the two write functions. But now that I have two write functions, each one of those can do a try-put command on the TLM FIFO. So these are TLM FIFOs, not TLM analysis FIFOs. So I can do the try-put commands on each of those TLM FIFOs to place the transactions into there. And so with these implementation ports, we also have to implement the write methods to take the transactions coming up to the implementation ports and push them onto the TLM FIFOs. The TLM FIFOs must be constructed to be unbounded to make sure the try-put command always works. And the TLM FIFOs do not have a UVM analysis implementation port on them, so they themselves could not terminate the analysis path. We brought it to another termination point, then used write methods to push those into the TLM FIFOs. And once again, inside of your scoreboard, you'll set up some type of little forever loop that's going to get the expected transaction, get the output transaction, run the comparisons to make sure that the design is working. Then you've got the style that uses the TLM analysis FIFO, and this is the one that Heath and I generally prefer. So you still have your agent, your monitor with an analysis port, agent with an analysis port, and it connects up to an analysis export, not an implementation, and export on the scoreboard. The scoreboard is really little more than a wrapper here. But then inside of the scoreboard, we put a predictor component that we typically extend from UVM subscriber. And by doing that, it means that we already have a built-in analysis implementation port, even though it's called analysis export. So it's built into our predictor right there. And inside the predictor, we produce the write function, because this write function is going to take the incoming transaction, look at the inputs, predict the output, generate a new expected transaction, and then it needs to broadcast it out of another analysis port over to the comparator. So on the comparator, we have two analysis exports, not implementations. They don't terminate the paths. A couple of exports, and we run the connections from the export on the scoreboard wrapper to the export on the comparator, and we also run the connection from the analysis port on the predictor to the other export on the comparator. Then inside of the comparator, we put two of the TLM analysis FIFOs. The TLM analysis FIFOs already have the built-in implementations in order to terminate our analysis paths. And so we can terminate both of those. The TLM analysis FIFOs are unbounded by default, and they also already have the built-in write methods. So they're going to take the transactions that were broadcast, push them onto the mailboxes. Then inside of the comparator, again, we set up our little forever loop that's doing an expected FIFO get and an output FIFO get. Wait until you have one of each, and then run your comparisons between those. So what about these transactions that are being created? Can we just modify them on the fly? Because we said in satellite TV, you're not allowed to modify the programs that are being broadcast from the satellite. You can take a copy and modify that. You can't modify the broadcast program. And so in the run phase of the monitor, what it does is it's sampling all the signals from the design, and then it's going to take the signals that have been put back into a transaction, and it's going to broadcast it up for the rest of the UVM test bench to see. And so we've created a new transaction, one that we just call TR number 1. That is going to be broadcast up to the coverage collector, but what is really broadcast up there is a handle to that TR1. It's not a new copy. And then similarly, it's going to come up to the predictor. It's going to make its way on over to the comparator, and it's going to be placed inside of the TLM FIFO. But again, these are all handles. They're not new copies of the transaction. And then from there, the forever loop is going to grab that handle out and use that data for comparison purposes. So the predictor has a write method that creates a new expected transaction. We don't want to be modifying the broadcast transaction. So instead, we need to take a copy of the transaction to create a new expected transaction. And that one is then broadcast over to the TLM FIFOs and finally also makes its way over to the forever loop. And the forever loop is looking at the handle of the expected transaction. And so really, you only have two transactions there, one out of the monitor and one out of the predictor. And so the rest of those are all handles that point to those transactions. And so again, the monitor samples a DUT, and it's going to broadcast the transaction. And so you'll see the second transaction broadcast throughout your test bench. And similarly, your predictor is going to take a copy of the second transaction, and then it's going to broadcast it into the TLM FIFO and on into the comparator. So this is why it is so important that you make sure that you are taking, before you modify anything in that transaction, you take a copy of it. Otherwise, you're modifying the transaction that everybody can see. So inside of that scoreboard, let's kind of compare TLM FIFOs to TLM analysis FIFOs. How are they used? Well, if you've got a TLM FIFO, it has a mailbox inside of it. It must be constructed to be unbounded. If you have a TLM analysis FIFO, it is already unbounded by default, and it also has the mailbox inside of it. If you're using the TLM FIFO, you typically have an analysis implementation port, whereas for the TLM analysis FIFO, you just have an analysis export that's going to come to it. With the analysis implementation port, we have to provide a write method that says, take the incoming transaction and try putting it into the TLM FIFO. With the TLM analysis FIFO, we just make a connection between the export and the implementation port because the TLM analysis FIFO already has the write method built in for us. So it'll take that broadcast transaction, store it inside of the mailbox. And then the TLM FIFO has the blocking get method, which is used frequently by the comparator. The same blocking get method is used by the TLM analysis FIFO. But those TLM analysis FIFOs are really nice for terminating paths without having to implement some type of write method. So ports and exports, okay, is the naming backwards? I mean, am I the only person that when I learned this stuff, it sounded like, shouldn't an export be a port and shouldn't a port be an export? I mean, an export is, shouldn't that be broadcasting this thing? This seems really backwards to me. And so had to come up with this little example right here. How do you think about ports and exports? Well, first off, when you get into an automobile, you know there's always going to be a steering wheel there. You know if you turn the wheel this way, car goes that way. Turn it the other way, car's going the other way. I don't know if that's rack and pinion, I don't know if that's fly-by-wire or some other mechanism. I know that an automobile has a steering wheel, and I can always count on one being there inside of the automobile. All of your automobiles also have an accelerator pedal. Push on the accelerator pedal, car's going to go faster. Let up on the accelerator pedal, you're going to coast and slow down. I don't know if that's fuel injection, carburation, or some type of electronic motor. I just know that every car is going to have an accelerator pedal. Every automobile is going to have a brake pedal. I know if I push on that brake pedal, the car is going to come to a stop. I know if I let up on the brake pedal, the car can be accelerated again. I don't know if I've got disc brakes, drum brakes, or some type of electronic recovery system. I just know that there's a brake pedal. I know inside of any automobile, I'm going to have a steering wheel, accelerator pedal, a brake pedal. I don't necessarily know how they work, but I know that I have the ability to use any of those as the driver of that car. If I get into a car, and I've got Bluetooth on my mobile phone there, and I want to use the Bluetooth phone connection capability in the car. If the car doesn't have it, I can't issue the command. Okay? I don't have access to Bluetooth in that car, so only if the car exports to me the capabilities that I want can I use them. So whenever I get into a car, I'm the initiator. The car is going to export to me the ability to steer, the ability to accelerate, and the ability to brake. And so whenever you've got a port and an export, the port can only issue commands that are being exported to it from the other end. And once I learned that, to say, okay, this isn't so bad. I can live with this. Okay. Let's talk about analysis path basics here a little bit. So how do analysis port paths work? And in the software world, these are called observer patterns. You have one broadcast source and a whole bunch of observers. We often refer to them as subscribers, someone who's looking at the transactions. So we've learned about analysis ports and TLM FIFOs. So you've already learned about analysis ports, analysis exports, analysis implementation ports, TLM FIFOs, TLM analysis FIFOs. What I'm about to describe right here is unnecessary information, unnecessary learning. And so if you're happy about how all these things work, you can say to yourself, no, I'm going to get an early start on lunch. I'll walk out right now and Cliff will not be offended. It's okay. You're allowed to do that. So you don't have to know how these things work. But we have found that the best engineers with UVM verification environments are ones that have some understanding of what's happening inside of UVM. So I'm going to share with you how, kind of at a high level, how this works. And so that's what the remaining slides are, to talk about how UVM makes subscribers work. And this is a very high level. This is not UVM code. Let's make that clear right now, that what I'm about to show you is nothing you have to do. This is all done for you inside of UVM. So when I go to the next slide and you say, gosh, do I have to do that in UVM? The answer is no. This has already been done for you. This is a basic version of what UVM does internally. And these slides show how UVM uses queues and for each loop to basically go through and execute all the write methods. Okay? This is a high-level tutorial on how these UVM paths and connections work. This is not exactly how UVM works, but it's close. So our goal is we want to create a monitor that can connect to any number of subscribers and can call a write method from each of the subscribers without modifying the monitor code. So there's the goal. I'm going to show you two versions. In the first version, we will not achieve the goal. In the first version, the top module must know subscriber handle names in the monitor. That's bad. So the monitor must declare each subscriber handle separately. That's bad. It will have no connect method to copy handles. So the handles have to be copied by name. That's bad. It must call a write method for each subscriber individually. Also bad. Well, let's fix all of that. In version 2, we'll have a monitor with a generic connect method to connect the subscriber handle names. This is good. The monitor will have a queue of subscriber handles, so we don't have to declare all of them. This is good. The monitor defines a common connect method for all the subscribers, so we don't have to know the internal names. And it'll use a for each loop to call the write methods for each connected subscriber. This is also good. And this is UVM-like. This is not what UVM exactly does, but it is UVM-like. So in the first version, we're going to have a monitor where we've declared 3 analysis interface handles called AP1 through AP3. It'll be from a virtual class called analysis interface. And this virtual class will have a pure virtual write method in it. Remember, pure virtual means that anything that extends this class has to provide the write method implementation. And so the first subscriber that will extend the UVM analysis interface will provide a write method in order to display that the subscriber has received a certain data member. And then we'll have a second subscriber that also extends the analysis interface with its own write method, and a third subscriber as well. Now, any extended handle can be copied to a base class handle. So we are going to copy to each of these analysis port handles each of these subscriber handles. And so we'll copy the sub1 handle to AP1, sub2 handle to AP2, sub3 handle to AP3. And so at the top level, we're going to need to know what are the handle names inside of the monitor so that we can copy our local handles to the monitor handle, the handles inside of that monitor. And so in this first version here, we've got a top module where we've declared a monitor handle and we new construct the monitor. Again, this is not UVM, so I'm not using the factory. This is not UVM code. Second, I'm going to declare 3 subscriber handles, and then I'm going to new construct each of those subscribers. Now, because I don't have a connect method, I needed to know what were the internal names inside of that monitor, so I can copy each of these subscriber handles to the monitor handles from the top module. So I had to make hierarchical references. I had to know those names. And then I call the monitor run task. And in the monitor run task, it's just going to repeat 5 times looping. It's going to display what the monitor transaction is, display that the monitor is broadcasting the transaction. And then once again, we had to know how many subscribers we had and had to call them each individually, we called the write method out of each of those monitors. So we must declare each handle separately. That's not very good for reuse. We have no connect method to hide the internal names. We must call each write method individually. And so in version 2, we're going to fix all of these issues. So in version 2, the first difference, well, first, the top module, nothing changed about that up until this point here. But then in the monitor, we're going to declare a queue of these analysis interface handles. And then we're also going to put in a generic connect method. So we can pass any analysis interface port, basically an upcast, and store it. We're going to push it back onto that analysis port queue. So we've got a queue right there, and we can push as many as we want onto the analysis port queue. Next, we're going to call the connect method and pass in the subscriber handles into the monitor. And so we still have to connect each of the subscribers to our monitor. But then we have a for each loop down inside of the run task. And the for each loop is just going to walk through all of the handles that have been stored in that queue, and it's going to call the write method that's in for each of those handles. Now remember, the analysis interface had a pure virtual write method, which means we know that every subscriber has to have a write method, and the prototype has to look exactly the same. So we can walk through all of the connected subscribers and execute their write methods. Basically, pass them the transaction, and they can decide what they want to do with it. Now I can put more subscribers on this monitor without modifying the monitor code at all. I can connect more at the top level. And so I now have a queue of analysis interface handles. That's good. I now have a common connect method to push these handles onto the queue. I have a for each loop that's going to walk through all those handles, and I know that each one has a write method. I will call the write method off of each of those subscribers. So our goal has been achieved. We now have monitor code where we can attach as many subscribers as we want without modifying any of the monitor code itself. This is what UVM does, but you don't have to do this in UVM. I want to make sure that you plainly understand this is not UVM code. This is what UVM does internally. You don't have to declare these queues. You don't have to put together your own connect method. You don't have to have a for each loop to walk through all the write methods. This is what happens when you start using analysis ports, paths, and implementations. Okay. So what we have here is we've got a top module that has a monitor in it, and it's going to sample a transaction and then broadcast the transaction. So when we run the simulation, we see that the transaction was randomized and that the monitor has broadcast that transaction. Then the write methods are going to be called, and each subscriber in this example, all they're doing is they're printing out that they have received the transaction and showing us what the data fields are. And so that's fine. So each subscriber has seen the next same address and data values because they've each been passed the same handle. Next, let's put a little bug into one of these examples. We have a subscriber that prints out that it's displaying that it is a subscriber and that it has received the information. The second subscriber will also display that it has received the address and data values, but if we turn on bug, then it's going to change the address and data values on the broadcast transaction. You're not supposed to do that. You're not supposed to change anything on a broadcast transaction. So instead, we've got the bug that is putting the values out there, which means the subscriber is going to display what the new values are. You should never modify a transaction that has been broadcast from an analysis port. Then the third subscriber is going to print out what it sees, and it's actually going to print out the buggy code because it happened to be called after the second subscriber. So the sub 3 sees the corrupted transaction and data. But not only that, so you see that we've randomized data, the monitor has broadcasted, the first subscriber has displayed that it received it, the second subscriber says it has received it, then it says, oh, but I have modified it, I've set the values, and then the third subscriber sees the modified values. It could be worse, depending on how those are queued in the subscriber queue. The first subscriber also might have seen the bug. It all depends on how they were queued up, whether you're going to see the correct values or not. All subscribers receive a handle to the same broadcast transaction. A subscriber should never modify the contents of the received transaction. It is an FCC violation to mess with any programs being sent from a satellite. And it is a severe problem to be modifying the fields of a transaction that has been broadcast to subscribers. You never modify those contents. Any subscriber that modifies transaction contents must take a copy before making modifications. And that's why in our scoreboard, in our predictor, before it predicted what the expected output should be, it took its own copy, looked at the inputs, then it could modify the outputs of its own copy of that transaction. Then the actual transaction and the expected transaction were both pushed into TLM analysis FIFOs so that the comparator could pull them off in order and run the comparisons. So, summary and conclusions. Analysis ports are ports that broadcast transactions to 0 or more destinations. Each subscriber chain terminates with an analysis implementation port and a corresponding write method. The corresponding write method says, once the transaction gets to me, what am I going to do with the transaction? That's what the write method is for. As an interesting side note, in UVM, the broadcast command, you say analysis port.write, and on the receiving side, you are going to declare a write method to say, what are you going to do with that transaction? In UVM, they really did not need to use a write command for the broadcast. That could have been called anything, broadcast, send, whatever you want, because and the good news is you only have to remember one command. There's a broadcast command and there's a write command to receive the broadcast. The downside is, for guys like me, I was trying to figure out how this write right here was calling this write over here, and it's not. This write command goes through a queue, and the queued handles call these write methods. And so it could have been called anything, but it has been called write, and so the names do match. Subscribers should never modify the broadcast transaction. And that is an FCC violation and a UVM violation. Subscribers need to use the transaction in 0 time, so when it is received, they either need to be watching it live or they need to put it on their DVR. They need to take a local copy before using the transaction. Okay? You can't come in late and say, would you please send that again? It doesn't happen. If a component has multiple implementation ports, you'll want to use the macro UVM analysis implementation declaration macro. And so this macro, you're going to say, what should the suffix be if you have multiple analysis implementation ports? And this isn't just for scoreboards. If you have any component that has multiple analysis implementation ports to it, you'll want to use this macro, you'll want to use these techniques. It'll give you different implementation macros with different suffix names and corresponding write methods with those suffix names as well. The UVM TLM analysis FIFO has the built-in UVM analysis implementation port. Unfortunately, it's called analysis export, so it's confusing. But it is an implementation port. The UVM TLM analysis FIFOs have the termination point for your analysis paths. And once you have that all together, you should prove that your scoreboard is working. You should break your design and make sure that the scoreboard can find the errors. Why do I say that? Because I spent 3 hours debugging one of these one time. And then I passed it on to Heath, because Heath's a verification expert, but he did it in an hour and a half. But still, it took us a while. And what we were doing is we were broadcasting transactions on an analysis path, but my predictor was modifying the outputs of the transaction. And so what happened is, once I put a bug into my design and I ran the simulation, it passed. So I put a bigger bug into the design, ran the simulation. It still passed. I brought up the waveform viewer and looked inside the interface, and I'm getting all the wrong data coming out of my design as expected, but once I get up to my scoreboard, everything's passing. Because what happened is, remember, this transaction is being broadcast. So what my predictor did is my predictor looked at the inputs, corrected the outputs, which was also on the other handle, and so they got over there, and now the output is corrected inside of the scoreboard, and that's wrong. And so whenever you do something like this, give yourself a little sanity check. That is, introduce some type of error. Make sure that your scoreboard can catch these types of errors. Okay. And there's my dirty laundry. All right. Okay, so resources, just by way of review. There's just a wealth of great information out on the Accelera webpage. You have access to the videos, you have access to the forums. Then you can register for the free DVCon 2017 and 2018 presentations by the really smart people on this stuff, not the average guy. And the really smart people will talk about some of the corner case advanced things that you can do with this. Also, You can access all of the forums on the Accelera webpage. A great place to be asking questions, a great place to look at questions that have already been asked. Get the free IEEE login. IEEE is not free, and most of us know that, but the login is free. And once you have an IEEE login, then you can gain access to the IEEE standard for System Verilog 2017 and the IEEE standard for UVM and the IEEE standard for System Verilog 2017. And so those documents are out there, but of course you just go to the Accelera webpage and it already has links to each of those documents. And so this is a wealth of information that is freely available to you. Take advantage of these resources that are out there. And I've been out to the Accelera webpage, lots of videos on lots of topics on that webpage. It's very good. Once you have the IEEE login, then you can download PDF versions of each of those standards. Without the login, you can view them online, but you can't download them. And I think that takes me just about up to my time. All right, thank you. Okay.